Space has always been the greatest mystery of all. No matter how much we learn about the universe, every answer leads to even deeper questions. For centuries, humanity has gazed at the stars, wondering what lies beyond our world. From ancient civilizations tracking the motion of the planets to modern telescopes revealing the secrets of distant galaxies, our understanding of the cosmos has evolved dramatically. Yet, despite our technological advancements, space remains an endless frontier filled with unanswered questions. What is the true nature of the universe? How did it begin? What forces shape the galaxies, stars, and planets? And perhaps the most intriguing question of all, are we alone in the vastness of space? Science has continuously reshaped our understanding of the cosmos. In ancient times, people believed Earth was the center of the universe, with the sun, moon, and stars revolving around it. But as our knowledge expanded, this idea was replaced by the heliocentric model, which revealed that Earth orbits the sun. Then, as telescopes improved, we discovered that our solar system was just one of billions in the Milky Way galaxy. And beyond that, we found an entire universe filled with countless galaxies, each containing billions of stars. Even today, with powerful space telescopes and advanced physics, we are still only scratching the surface of the universe's secrets. The vastness of space is difficult to comprehend. The distances involved are so immense that we measure them in light years. The distance light travels in 1 year, which is nearly 10 trillion kilometers. To put this into perspective, the moon is just over 1 light second away, meaning light takes a little over a second to travel from Earth to the moon. The sun, on the other hand, is about 8 light minutes away. But when we look at the closest star beyond our solar system, Proxima Centauri, we are seeing it as it was over 4 years ago because it is 4 light years away. The farther we look, the further back in time we see. Some of the galaxies we observe today are so distant that their light has taken billions of years to reach us, meaning we are seeing them as they were billions of years ago. The observable universe is estimated to be about 93 billion light years wide, but beyond that, there could be an infinite expanse of space that we will never see. Humanity has always been driven by curiosity and the need to explore. From the first humans who left Africa in search of new lands, to the astronauts who set foot on the moon, exploration is in our nature. The same curiosity that led sailors to cross oceans and mountaineers to climb the highest peaks now drives scientists to explore the cosmos. Space exploration is not just about satisfying curiosity, it also leads to technological advancements that benefit life on Earth. Satellites enable global communication, weather prediction, and navigation. Space missions provide insight into planetary climates, which helps us understand our own changing environment. Even medical technologies, such as imaging techniques used in hospitals, were developed from space research. The quest to understand the universe is deeply connected to our progress as a species. In this 3-hour journey, we will uncover the most mind-blowing aspects of space. We will explore the vastness of the cosmos, the countless stars scattered throughout the universe, and the strange and extreme planets orbiting them. We will dive into the mysteries of our own solar system, uncovering bizarre phenomena that challenge our understanding of physics. We will seek answers to the greatest cosmic questions. What are black holes? And what happens if you fall into one? Could alien life exist on other planets? Why have we never encountered extraterrestrials? And how will the universe ultimately end? These are some of the fundamental mysteries that scientists have been trying to solve for decades. Throughout this journey, we will separate fact from fiction. Science fiction has often imagined interstellar travel, wormholes, and parallel universes. Some of these concepts are purely speculative, while others are based on real physics. Black holes, once considered science fiction, have been proven to exist, and we have even captured an image of one. Wormholes, on the other hand, remain hypothetical, but scientists continue to explore their possibility. The multiverse is an idea that stretches the limits of our imagination, yet some theories suggest it could be real. As we embark on this cosmic adventure, we will examine what is scientifically possible and what remains purely speculative. Understanding space requires us to grasp the sheer scale of the universe. Our planet is just a tiny speck in the vast cosmic ocean. Even our entire solar system is insignificant compared to the Milky Way galaxy, which is just one of billions of galaxies scattered throughout the universe. The deeper we look, the more we realize how small we are in the grand scheme of things. And yet, despite our smallness, we are able to ask these big questions. We have the tools to study the universe, the intelligence to interpret its secrets, and the curiosity to keep searching for answers. This is just the beginning of our journey into the unknown. As we continue, we will explore the unimaginable vastness of the cosmos, revealing the mind-boggling scale of everything that exists. From the smallest particles that make up reality to the largest structures in the universe, every discovery brings us closer to understanding our place in the cosmos. Let's start by understanding the sheer scale of the universe. When we look at the night sky, it is easy to feel small. We see distant stars, glowing planets, and perhaps even the faint band of the Milky Way stretching across the horizon. But no matter how immense the cosmos appears to us, the truth is that it is far larger than we can possibly comprehend. Scientists estimate that the observable universe stretches roughly 93 billion light-years across. This number alone is difficult to grasp, but what makes it even more astonishing is that this is only the part we can see. Beyond this, the universe may continue indefinitely, stretching far beyond the limits of our perception. The observable universe is a concept based on the limitations of the speed of light. Because light takes time to travel through space, we can only see as far as light has had time to reach us since the beginning of the universe. This means that when we observe distant galaxies, we are looking back in time. A galaxy 10 billion light-years away appears to us as it was 10 billion years ago, when the universe itself was still in its infancy. As a result, the night sky is not just a glimpse of the present, it is a window into the past. Yet, despite how far we can see, there is far more that remains hidden. The universe is constantly expanding, and as it does, some galaxies move away from us at speeds faster than light due to the stretching of space itself. Because of this, some parts of the universe will never be visible to us, no matter how powerful our telescopes become. In the distant future, this problem will become even more severe. Billions of years from now, many of the galaxies we see today will have receded beyond our observable horizon, vanishing from view forever. If intelligent civilizations emerge in that distant era, they may believe they exist in a nearly empty universe, completely unaware of the vast cosmos that once surrounded them. To truly understand the sheer scale of the universe, let us break it down into something more relatable. Imagine the Sun, the massive star at the center of our solar system. Now, shrink it down to the size of a single grain of sand. At this scale, Earth would be an invisible speck orbiting nearby. The entire solar system, including all the planets, would be about the size of a dinner plate. But what about the distance to the nearest star? In this comparison, Proxima Centauri, the closest known star to the Sun, would be another grain of sand over 4 kilometers away. Now consider the Milky Way galaxy. It contains hundreds of billions of stars, all separated by vast distances. And at this scale, it would stretch across entire continents. But even the Milky Way is just one of billions of galaxies in the universe. If we continued this analogy, the observable universe itself would be larger than the entire planet, and possibly even beyond. But even galaxies do not exist in isolation. They are grouped into clusters and superclusters, bound together by gravity into enormous structures. The Laniakea supercluster, the massive collection of galaxies that includes the Milky Way, stretches over 500 million light-years across. Yet, even this pales in comparison to the largest structures ever discovered. The Hercules Corona Borealis Great Wall, a massive assembly of galaxies, spans a staggering 10 billion light-years. Structures of this size challenge our understanding of how the universe formed. According to our current models, galaxies should not be able to clump together on such large scales, leading scientists to question whether our understanding of cosmic evolution is truly complete. Throughout history, our perception of the universe's size has changed dramatically. In ancient times, people believed Earth was the center of the universe, with the sun, moon, and stars revolving around it. As our knowledge grew, we realized that Earth orbits the sun, that the sun is just one of many stars, and that our Milky Way is only one of countless galaxies. Even now, with all we have learned, we are still only scratching the surface of what exists in the cosmos. One of the greatest revelations in modern astronomy has been the discovery that the universe is constantly expanding. In the early 20th century, astronomer Edwin Hubble made a groundbreaking observation. Nearly all galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. This discovery led to the realization that space itself is stretching over time. If we reverse this expansion, we arrive at a single point where everything in the universe was once compressed, an idea that became the foundation of the Big Bang Theory. Yet, even with the knowledge of expansion, we do not know the true size of the universe. The 93 billion light-years that define the observable universe are merely the distance light has had time to travel since the Big Bang. But what lies beyond? Many scientists believe that the actual universe could be at least hundreds of times larger than the observable portion. Some theories even suggest that it is truly infinite, stretching forever in all directions. If this is the case, then no matter how advanced our technology becomes, we will never be able to see the full extent of reality. Our ability to observe the universe is shaped by technology. The Hubble Space Telescope gave us some of the deepest images of space ever captured, revealing galaxies billions of light years away. Now, the James Webb Space Telescope is pushing the boundaries even further, allowing us to see fainter and older objects than ever before. Future telescopes, both on the ground and in space, will continue to reveal more of the cosmos. Yet, no matter how powerful our instruments become, the expansion of the universe ensures that some regions will always remain hidden. Despite these limitations, we continue to discover more about the vast cosmos around us. Every new observation brings us closer to understanding the grand structure of the universe. We now know that galaxies are not randomly scattered, but are arranged in massive, interconnected networks. Cosmic filaments, vast threads of dark matter and galaxies, weave through space, forming a structure often compared to a cosmic web. In between these filaments are immense voids, regions of space that contain very few galaxies at all. These cosmic voids are among the most mysterious aspects of the universe, raising questions about how such vast, empty spaces could have formed. And yet, within this unfathomable vastness we exist, on a tiny, rocky planet orbiting a single star in an ordinary galaxy. This realization puts our place in the universe into perspective. We are a mere speck in a cosmic ocean, so immense that even light itself takes billions of years to traverse it. And yet, within this small corner of the cosmos, we have the ability to explore, to question, and to seek answers. The vastness of the universe is not just humbling, it is also a reminder of how much more there is left to discover. Now, as we continue our journey, we must ask, just how many stars exist in this vast universe? When we gaze up at the night sky, we see only a fraction of the stars that exist in the universe. The Milky Way, our home galaxy, is estimated to contain between 200 billion and 400 billion stars. Yet, the Milky Way is just one of billions of galaxies spread throughout the universe, each filled with its own countless stars. If we take a step back and attempt to count all the stars in the cosmos, we arrive at an almost unimaginable number, one that dwarfs anything we experience in everyday life. Scientists estimate that the observable universe contains at least 1 septillion stars, a number written as a 1 followed by 24 zeros. To put this into perspective, this is more stars than all the grains of sand on Earth. If we were to gather every grain of sand from every desert, every beach, and every ocean floor, the total number would still be less than the number of stars shining across the cosmos. It is a number so vast that the human brain struggles to truly comprehend its scale. Let us break it down in a way that makes sense. Suppose you decided to count every star in the universe. Even if you could count at a rate of 1 star per second, it would take over 30 million years to finish. And that is just the number of stars in the observable universe, the part of the cosmos we can see. If the universe extends far beyond what we can detect, as many scientists suspect, the true number of stars could be even greater. Stars are not evenly distributed throughout space. Instead, they are organized into massive galaxies, each containing billions or even trillions of individual stars. These galaxies, in turn, are not randomly scattered but form enormous clusters and superclusters that stretch for hundreds of millions of light years. At the largest scales, galaxies are connected by vast cosmic filaments, forming a cosmic web, a structure resembling a vast, interconnected network of glowing threads in the darkness. This immense network of galaxies, stars, and dark matter spans the universe, with enormous empty voids in between, where very few stars exist. The way we estimate the total number of stars in the universe relies on our understanding of galaxies. When we look at galaxies close to us, we can estimate the number of stars they contain by studying their brightness and size. We then assume that galaxies farther away follow similar patterns. However, there is a challenge. Because light takes time to travel, when we look at distant galaxies, we are seeing them as they were billions of years ago. Some of these galaxies have changed, merged, or disappeared entirely since the light left them. This means our calculations are based on an ever-changing cosmic landscape. Another complication is that many stars are not visible to us. Some stars are too faint, hidden behind cosmic dust, or obscured by their own galaxies. Others are located in regions of space so distant that their light has not yet reached us. The James Webb Space Telescope has helped us see deeper into the universe than ever before, but even it cannot reveal every hidden star. Despite these challenges, astronomers have made incredible progress in understanding the nature of stars. They have classified stars based on their size, temperature, and brightness, ranging from tiny red dwarfs, which are the most common type of star in the universe, to massive blue supergiants that shine with incredible intensity but burn out quickly. Stars are born from giant clouds of gas and dust, forming in stellar nurseries where gravity pulls matter together until nuclear fusion ignites. Over millions or even billions of years, stars evolve, sometimes becoming red giants, then collapsing into white dwarfs, neutron stars, or even black holes. Some of the most spectacular stars in the universe exist in the form of binary or multiple star systems, where two or more stars orbit each other. In some cases, stars in these systems exchange matter, creating powerful stellar winds and explosions that shape their surroundings. Other stars exist in dense clusters, where thousands or even millions of stars are packed closely together, creating some of the most breathtaking regions of space. One of the most mind-boggling aspects of counting stars is that new stars are always forming while old stars are dying. In the Milky Way alone, it is estimated that about one new star is born every year, while others reach the end of their life cycles and either fade away or explode in spectacular supernova. This means that the number of stars in the universe is not static. It is constantly shifting as the cosmos evolves. Another fascinating aspect of star formation is the role of dark matter, the invisible substance that makes up most of the universe's mass. Although we cannot see dark matter directly, its gravitational influence plays a crucial role in shaping galaxies and guiding the formation of stars. Without dark matter, galaxies would not hold together, and the universe as we know it might not exist. As we continue to refine our understanding of the universe, we may one day discover even more stars than we currently estimate. Some theories suggest that in the vast empty spaces between galaxies, there may be rogue stars, stars that have been ejected from their home galaxies and now drift alone in intergalactic space. These lonely stars may never be counted, but they are a reminder that the universe is full of mysteries waiting to be uncovered. The vastness of space, filled with countless stars, makes it clear that our own planet is just a tiny speck in an unimaginably large universe. Yet, despite our smallness, we have developed the ability to study the cosmos, to peer into the depths of space, and to ask profound questions about our existence. Every star represents a potential new world, a place where planets may orbit, where life might arise, or where civilizations could be waiting to be discovered. Now that we understand just how many stars fill the universe, the next question is, what kind of planets orbit these stars? Among the countless solar systems scattered across the cosmos, some planets are unlike anything we have ever imagined. Some are made entirely of diamond, others rain molten iron, and some exist in environments so extreme that they defy the very laws of physics. As we continue our journey, let us explore some of the most bizarre and fascinating worlds ever discovered. Our understanding of planets has evolved dramatically over the last few decades. For centuries, the only planets we knew of were those in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But with the advent of more advanced telescopes and exoplanet hunting missions like the Kepler Space Telescope, we have discovered thousands of planets beyond our solar system. Many of them are unlike anything we could have ever imagined. Some of these planets defy the very rules of physics as we know them. Others exist in conditions that seem more like the setting of a science fiction story than real astronomical objects. There are planets made of diamond, planets where it rains molten glass sideways, planets that orbit two suns, and even planets that might be entirely covered by deep global oceans. One of the most fascinating planets ever discovered is 55 Cancri e, located about 40 light-years from Earth in the constellation Cancer. This planet is a super-Earth, meaning it is larger than Earth but smaller than Neptune. What makes it extraordinary is that scientists believe it may be composed primarily of diamond. This idea comes from the fact that 55 Cancri e orbits a star that is much richer in carbon than our Sun. Because of the planet's proximity to its star, it experiences extreme heat, with surface temperatures reaching nearly 2000 degrees Celsius. Under such extreme conditions, and with an abundance of carbon, planetary formation models suggest that instead of having a rocky surface like Earth, this planet could be a solid chunk of diamond, a planet-sized jewel floating in space. If this theory is correct, then 55 Cancri e would be worth more than the entire economy of Earth many times over. But of course, it is completely unreachable with our current technology. Even if we could travel there, mining an entire planet of diamond would present engineering challenges beyond anything humanity has ever attempted. If there is a planet that sounds like the setting for a nightmarish sci-fi world, it is HD 189733b, a gas giant located about 63 light-years from Earth in the constellation Vulpecula. This planet is classified as a hot Jupiter, meaning it is a gas giant like Jupiter, but orbits extremely close to its star. The most terrifying feature of HD 189733b is its weather. The planet is tidally locked, meaning one side always faces its star, while the other remains in eternal darkness. On the day side, temperatures soar above 1700 degrees Celsius, hot enough to turn silicate particles into molten glass. These particles are carried up into the planet's upper atmosphere, where they form glass clouds. But here is where it gets even stranger. HD 189733b has winds that blow at over 8,000 km/h, 7 times faster than the speed of sound. These winds carry the molten glass sideways, creating a planet where it literally rains glass in horizontal sheets, shredding anything that would dare enter its atmosphere. In the Star Wars universe, the planet Tatooine is famous for having 2 suns in the sky. While this concept might have once seemed purely fictional, astronomers have discovered that planets orbiting binary stars, systems with 2 suns, are actually fairly common. One of the most well-known examples is Kepler 16b, a Saturn-sized gas giant that orbits 2 stars. This means that if you were standing on the surface of Kepler 16b, you would see 2 suns rising and setting each day. The interplay between these 2 stars creates a constantly shifting light pattern, unlike anything we experience on Earth. However, unlike the scorching deserts of Tatooine in Star Wars, Kepler 16b is actually very cold, with temperatures dropping below -100 degrees Celsius. Despite orbiting 2 stars, it is too far away from them to receive enough heat to sustain liquid water. Kepler-16b is a gas giant, meaning it has no solid surface. But it is entirely possible that rocky moons orbiting the planet could be habitable. If one of these moons had the right conditions, it could theoretically support life, making this system one of the most fascinating places to study. Among the strangest planets ever discovered is GJ1214b, a world that appears to be covered in a deep, global ocean with no landmasses at all. Located about 48 light-years away, this planet is classified as a mini Neptune, meaning it is smaller than Neptune, but still much larger than Earth. What makes this planet unique is that its density suggests it is composed mostly of water. Unlike Earth, where water covers about 70% of the surface but is still limited to oceans, lakes and rivers, GJ1214b may be entirely covered in water, a planet-wide ocean thousands of kilometers deep. The conditions on this planet are unlike anything found on Earth. The immense pressure at the bottom of its deep oceans could create exotic states of water, such as hot ice or superfluid water, where water behaves in ways that are impossible on Earth. Some scientists believe that if there is life beyond Earth, planets like GJ1214b might be the perfect candidates. If complex life can thrive in Earth's deep oceans, where no sunlight reaches, then perhaps alien life could exist in the vast, unbroken seas of an exoplanet like this. Planets like 55, Cancri E, HD 189733b, Kepler-16b, and GJ1214b are just a small sample of the incredibly diverse range of worlds that exist beyond our solar system. Many of these planets challenge our understanding of physics and chemistry. For example, some planets orbit so close to their stars that they are literally evaporating, their atmospheres being stripped away by intense radiation. Others exist in rogue orbits, drifting through space with no parent star, doomed to an endless journey through the cosmos in perpetual darkness. Some planets, known as puffy planets, have atmospheres so bloated that they are larger than Jupiter but lighter than cotton candy. Others are composed almost entirely of metal, with surfaces so reflective that they shine like mirrors. The search for exoplanets has revolutionized our understanding of the universe. The first confirmed exoplanets were discovered in the 1990s, and since then, thousands have been detected using advanced techniques like the transit method and radial velocity measurements. The Kepler Space Telescope alone discovered over 2,600 exoplanets, proving that planets are common throughout the galaxy. Now, with more advanced telescopes like the James Webb Space Telescope, we are beginning to analyze the atmospheres of exoplanets, searching for signs of life. Each new discovery pushes the boundaries of what we think is possible. Every strange planet tells a story about how unique and diverse the universe truly is. As fascinating as these exoplanets are, there is still much to uncover about our own solar system. Even though we have studied it for centuries, it hides some of the most shocking secrets in all of astronomy. Let us now turn our attention to the bizarre and unexplained mysteries of our own cosmic backyard. Our solar system is full of incredible and often bizarre facts that challenge our understanding of planetary science. For centuries, it was believed that our solar system was an orderly arrangement of planets revolving around the Sun, each following predictable paths and behaving in a way that seemed natural. However, as scientific knowledge expanded, we began to uncover just how strange our cosmic neighborhood really is. Some of these oddities are the result of physics, while others are remnants of chaotic events from the early days of the solar system. The planets, moons, and even the Sun itself have unique and unexpected features that continue to amaze scientists and astronomers alike. One of the strangest and most fascinating aspects of our solar system is Jupiter's influence on the Sun. Most people assume that the Sun is the absolute center of the solar system, with all planets, including Jupiter, simply orbiting around it. However, Jupiter is so massive that it does not technically orbit the exact center of the Sun. Instead, Jupiter's immense gravity tugs at the Sun so strongly that it actually causes the Sun to wobble slightly. This is because both Jupiter and the Sun orbit a shared center of mass, called the barycenter, which is located just outside the Sun's surface. The Sun does not sit motionless at the center of the solar system. Instead, it moves in a very subtle but measurable way due to Jupiter's gravitational pull. This effect is one of the ways astronomers detect exoplanets around other stars. By observing how a star wobbles due to an unseen planet's gravity, scientists can determine the presence and size of exoplanets orbiting distant suns. While Jupiter's gravitational influence on the Sun is remarkable, it is not the only planet with strange and unexpected behavior. Venus, the second planet from the Sun, has an extreme and counterintuitive climate. One would naturally assume that Mercury, being the closest planet to the Sun, should be the hottest. However, Venus holds the record for the hottest surface temperature of any planet in the solar system. The reason for this lies in Venus's thick atmosphere, which is composed mostly of carbon dioxide, with thick clouds of sulfuric acid. This dense atmosphere creates a runaway greenhouse effect, trapping heat so effectively that surface temperatures reach nearly 500 degrees Celsius, hot enough to melt lead. In contrast, Mercury, which is much closer to the Sun, lacks an atmosphere thick enough to retain heat, meaning it experiences extreme temperature fluctuations. During the day, Mercury's surface can heat up to 400 degrees Celsius, but at night, it plummets to negative 170 degrees Celsius. Venus, on the other hand, remains at a scorching temperature both day and night, making it even more inhospitable than Mercury. While Venus's atmosphere makes it a hellish world, Uranus has an even stranger characteristic. It rotates on its side. Unlike every other planet in the solar system, which spins relatively upright on their axes, Uranus is tilted at an extreme 98-degree angle. This means that for long periods of time, one pole of Uranus is pointed directly at the Sun, while the other is in total darkness. Scientists believe that this extreme tilt was caused by a massive collision in the early solar system. Billions of years ago, Uranus may have been struck by an Earth-sized or even larger object, knocking it onto its side and fundamentally changing its rotation. This event would have also disrupted any early moons or rings Uranus had at the time. Today, Uranus continues to spin in this unusual orientation, with seasons that last for decades due to its long, 84-year orbit around the Sun. The oddities of planetary orbits do not stop with Uranus. Pluto, once considered the 9th planet of the solar system, has one of the most unusual orbits of any celestial body in our cosmic neighborhood. Unlike the planets, which all follow relatively circular orbits around the Sun, Pluto's orbit is highly elliptical and tilted compared to the plane in which the planets orbit. This means that Pluto's path takes it much closer to the Sun at certain times and much farther away at others. In fact, for about 20 years of its 248-year orbit, Pluto is actually closer to the Sun than Neptune. Because of this irregular orbit, Pluto's position relative to the other planets constantly shifts, making its motion far more unpredictable than any of the major planets. This chaotic orbit is one of the reasons Pluto was eventually reclassified as a dwarf planet. It simply does not behave like the other planets in the solar system. Another peculiar feature of our solar system is the asteroid belt, a region between Mars and Jupiter filled with countless rocky objects. For a long time, astronomers speculated that the asteroid belt was the remnants of a destroyed planet or the early building blocks of one that never formed. However, further research suggests that Jupiter's immense gravity prevented these asteroids from ever coalescing into a planet. In the early days of the solar system, when planets were still forming, material in the region between Mars and Jupiter was constantly pulled and disrupted by Jupiter's gravitational influence. This prevented the rocks from sticking together and forming a planet, leaving behind a chaotic, scattered region of debris. Today, the asteroid belt contains everything from small pebbles to dwarf planets like Ceres, but it remains an example of how gravity can shape the formation of celestial bodies in unexpected ways. Jupiter's gravitational influence extends far beyond just the asteroid belt. It has been referred to as the solar system's vacuum cleaner because of its ability to pull in or deflect comets and asteroids that might otherwise pose a threat to Earth. Its immense gravity can capture comets, altering their orbits or sending them hurtling toward the inner solar system. In some cases, Jupiter has actually saved Earth from potential asteroid impacts by absorbing these cosmic threats. One of the most dramatic examples occurred in 1994, when the comet Shoemaker-Levy 9 was pulled apart by Jupiter's gravity and then crashed into the gas giant in a spectacular series of explosions. The event was observed by telescopes around the world and served as a reminder of just how powerful Jupiter's gravitational influence really is. Another odd fact about our solar system involves its largest moon, Ganymede, which orbits Jupiter. Ganymede is not only the largest moon in the solar system, but it is even larger than the planet Mercury. Despite being classified as a moon, it possesses characteristics that make it almost like a planet in its own right. Ganymede has its own magnetic field, something no other moon possesses, and scientists believe it may have an underground ocean beneath its icy crust. If this ocean exists, it could contain more water than all of Earth's oceans combined, making it a prime candidate for future exploration in the search for extraterrestrial life. The moons of the solar system, in general, present some of the most intriguing and bizarre features known to science. Saturn's moon Titan, for instance, is the only moon in the solar system with a thick atmosphere. Not only does it have an atmosphere, but it also has liquid lakes, though not of water, but rather of liquid methane and ethane. Due to Titan's extremely cold temperatures, these hydrocarbons exist in liquid form, creating alien landscapes with rivers, lakes, and even rain. It is one of the few places in the solar system where a liquid cycle, similar to Earth's water cycle, is actively occurring. From Jupiter's immense influence to Venus's extreme heat, from Uranus's sideways rotation to the chaotic orbit of Pluto, our solar system is filled with strange and fascinating facts. Each discovery further proves that the solar system is not just a simple arrangement of planets orbiting the Sun, but rather a dynamic and ever-changing collection of celestial bodies with unique histories and extraordinary characteristics. The more we study these worlds, the more we realize that they have undergone countless collisions, transformations, and dramatic events throughout their history. Speaking of collisions, one of the most significant events in the history of our solar system involves our very own moon. Scientists believe that the moon itself was formed through a violent impact in the early days of the solar system. Understanding this history gives us deeper insight into the forces that shaped not just our planet, but the entire cosmos. The moon has been a constant companion to Earth for billions of years, influencing everything from our tides to the very stability of our planet. But its origin story is one of the most violent events in Earth's history, a tale of cosmic destruction and creation. Scientists now believe that the moon was born from a cataclysmic collision between Earth and a Mars-sized object billions of years ago. This event, known as the Giant Impact Hypothesis, suggests that a planet-sized body, sometimes referred to as Theia, smashed into the young Earth with unimaginable force. The impact would have been so powerful that it sent molten debris hurtling into space, forming a ring of material around Earth. Over time, this debris clumped together, eventually solidifying into the moon. Evidence supporting this theory comes from the analysis of moon rocks brought back by Apollo astronauts. These samples show that the moon's composition is remarkably similar to Earth's outer layers, suggesting that both bodies share a common origin. However, there are also key differences. The moon is almost entirely devoid of volatile elements, substances that evaporate easily, indicating that it was formed from material that had been superheated and vaporized, consistent with the idea of a massive collision. Computer simulations of such an impact also align with what we observe today, a relatively large moon orbiting Earth at a distance that makes sense given the energy involved in such an event. Beyond its dramatic formation, the moon plays a crucial role in shaping life on Earth. One of its most significant effects is its influence on our planet's tides. The moon's gravitational pull creates ocean tides by drawing water toward it as Earth rotates. Without the moon's gravity, tides would be much weaker, dramatically affecting marine life that has evolved to rely on the constant ebb and flow of the ocean. Some scientists even speculate that life on Earth may have first emerged in tidal pools, where the repeated movement of water could have played a role in the formation of complex organic molecules. The Moon also stabilizes Earth's axial tilt, which in turn regulates our climate. Earth's tilt is responsible for our seasons, and without the Moon's gravitational influence, that tilt could vary wildly over time. Some planets, like Mars, have experienced dramatic changes in their axial tilt, leading to extreme climate shifts. But thanks to the Moon, Earth's tilt remains relatively stable, helping to maintain a consistent climate over millions of years. This stability has been crucial for the evolution of life, as drastic and unpredictable climate changes would have made it much harder for species to survive and adapt. Despite being a steady presence in our sky, the Moon is not actually fixed in place. It is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. This might not sound like much, but over millions of years, it will have noticeable effects. As the Moon moves farther away, its gravitational influence on Earth will weaken. This means that tides will become less extreme, which could disrupt marine ecosystems that depend on the current tidal patterns. Additionally, the length of Earth's day is gradually increasing because of this process. In the distant future, a day on Earth will be significantly longer than the 24-hour cycle we experience today. If the Moon were to continue drifting away indefinitely, it could eventually reach a point where it no longer stabilizes Earth's tilt, leading to chaotic shifts in climate. However, this scenario is billions of years in the future, so it is not an immediate concern. While the Moon may appear lifeless today, it was once a far more geologically active place. Scientists have found evidence that the Moon once experienced volcanic activity, with lava flowing across its surface. The dark patches we see on the Moon, called lunar maria, are actually ancient lava plains formed by volcanic eruptions billions of years ago. These eruptions were likely caused by the intense heat trapped inside the Moon shortly after its formation. As the Moon gradually cooled over time, volcanic activity slowed and eventually ceased. However, some evidence suggests that minor volcanic activity may have continued for longer than previously thought. Recent discoveries have also revealed that the Moon is not as dry and barren as once believed. Water ice has been detected in permanently shadowed craters near the lunar poles, where temperatures remain extremely cold. This discovery has major implications for future space exploration, as lunar ice could be used to provide drinking water and even be converted into rocket fuel. If humans establish a permanent presence on the Moon, these ice deposits could be a crucial resource. The Moon's history is one of cosmic violence, transformation, and ongoing change. It has shaped Earth in profound ways, from stabilizing our climate to influencing the rise and fall of ocean tides. As we continue to study the Moon, we learn more about the history of our own planet and the solar system as a whole. Understanding the Moon's origins and evolution also helps scientists refine their theories about how planetary systems form and develop. If a massive collision could create the Moon, could similar impacts have played a role in shaping other planets? Some researchers believe that events like the one that formed the Moon may have also played a role in creating conditions suitable for life elsewhere. If a planet in another solar system experienced a similar collision, it might have resulted in the formation of a large moon that stabilizes its climate, just as our Moon does for Earth. This raises intriguing possibilities about the role moons could play in making exoplanets habitable. But the search for life in our solar system does not end with Earth and its Moon. Some of the most exciting possibilities for extraterrestrial life lie hidden beneath the icy crusts of distant moons. Moons like Europa and Enceladus are believed to harbor vast oceans beneath their frozen surfaces, making them prime targets for the search for alien life. Unlike Earth, where life depends on sunlight, these moons could support life forms that rely on heat from their planet's core, much like the deep-sea hydrothermal vents on Earth. If life exists in these hidden oceans, it would suggest that life can emerge in environments far different from what we are familiar with. The possibility of life beyond Earth has fascinated humans for centuries, and as we explore our own solar system, we are beginning to understand just how many worlds might be capable of supporting life. Whether it is a moon orbiting a gas giant or a distant exoplanet in another star system, the conditions for life may not be as rare as we once thought. If we ever discover extraterrestrial life, it may fundamentally change our understanding of the universe and our place within it. Our journey through space continues to reveal surprises, challenging what we thought we knew about our solar system and the wider universe. The moon, once thought to be just a lifeless rock orbiting Earth, has proven to be an essential part of our planet's history and stability. But beyond our moon, other celestial bodies may hold even more astonishing secrets. As we look beyond Earth's immediate neighborhood, we begin to wonder, could there be alien life within our own solar system, hiding in the icy depths of distant moons or beneath the surface of Mars? The search for extraterrestrial life has long been one of humanity's greatest fascinations. While we often look to the distant stars for habitable planets, some of the most promising places for alien life might actually exist within our own solar system. Though Earth is the only planet known to support life, there are several celestial bodies that have conditions where microbial organisms could potentially survive. From frozen moons hiding vast oceans beneath their surfaces to planets that once had rivers and lakes, the solar system holds several intriguing possibilities. If life does exist beyond Earth, it may not look like the intelligent beings we often imagine, but rather microscopic organisms thriving in extreme environments. One of the most promising candidates for extraterrestrial life is Europa, one of Jupiter's largest moons. Beneath its thick layer of ice lies a massive subsurface ocean, potentially containing more than twice the amount of water found on Earth. This vast body of water is kept in a liquid state due to tidal heating. Gravitational forces from Jupiter stretch and compress Europa's interior, generating enough heat to prevent the ocean from freezing completely. Scientists believe that this ocean could contain the key ingredients for life: liquid water, essential chemical compounds, and an energy source. On Earth, deep-sea hydrothermal vents support entire ecosystems of organisms that do not rely on sunlight for survival, instead using heat and minerals from the Earth's interior. A similar process could be happening on Europa, where hydrothermal vents at the ocean floor may provide energy for microbial life. Enceladus, a small but active moon of Saturn, is another prime candidate for alien life. Like Europa, Enceladus has a subsurface ocean hidden beneath a layer of ice. However, what makes this moon particularly exciting is that it actively releases plumes of water vapor into space. These geysers, which were first discovered by NASA's Cassini spacecraft, erupt from cracks in the icy surface, carrying organic molecules and other complex compounds. This means that Enceladus not only has liquid water, but also the essential building blocks of life. The presence of these organic compounds raises the possibility that microbial life could exist within its ocean, much like bacteria found in Earth's deep-sea environments. Future missions may focus on flying through these plumes to directly analyze their composition, searching for signs of biological activity. While Europa and Enceladus are often at the forefront of discussions about alien life, Saturn's largest moon, Titan, offers a completely different possibility. Unlike any other moon in the solar system, Titan has a thick atmosphere rich in nitrogen, similar to Earth's atmosphere billions of years ago. However, instead of water, Titan's surface is covered with lakes and rivers of liquid methane and ethane. The temperatures on Titan are far too cold for liquid water to exist on the surface, but scientists speculate that some forms of life, completely different from anything we know, could potentially survive in methane-based environments. On Earth, all known life is carbon-based and relies on water as a solvent. But Titan challenges this assumption, prompting scientists to consider whether alien life might evolve using an entirely different chemical foundation. If methane-based life exists, it would completely reshape our understanding of biology and what conditions are necessary for life to emerge. Mars, often called Earth's sister planet, has been at the center of the search for extraterrestrial life for decades. Though the red planet is a barren desert today, it once had a very different climate. Billions of years ago, Mars had a thick atmosphere and was covered with rivers, lakes, and possibly even an ocean. Evidence of these ancient waterways can still be seen in the form of dried-up riverbeds and lake basins. Scientists believe that during this period, Mars may have been capable of supporting microbial life. If life once existed on Mars, there is a possibility that some of it could have survived beneath the surface, where liquid water may still exist in underground reservoirs. Recent discoveries of methane emissions on Mars have further fueled speculation, as methane is often produced by biological processes on Earth. While it is possible that these emissions have a geological origin, they remain one of the most intriguing clues in the search for Martian life. The study of extremophiles, organisms that thrive in extreme environments, has significantly expanded our understanding of where life could exist. On Earth, we have discovered bacteria living in boiling hot springs, acidic lakes, and even deep underground, where sunlight never reaches. Some microbes survive in environments with no oxygen, instead using sulfur or other chemicals to generate energy. If life can persist in these extreme conditions on Earth, it is possible that similar organisms could be living on Europa, Enceladus, or even Mars. Studying extremophiles provides valuable insights into the types of alien life we might find and how they could survive in the harsh conditions of other planets and moons. As our technology advances, so do our efforts to find life beyond Earth. NASA and other space agencies have planned multiple missions to investigate these promising locations. The Europa Clipper mission, set to launch in the next few years, will orbit Jupiter and conduct multiple flybys of Europa, scanning its ice shell and searching for signs of life. A future lander could drill through the ice to directly sample the subsurface ocean. Meanwhile, robotic missions like the Perseverance rover are currently exploring Mars, searching for ancient microbial fossils and analyzing samples that may one day be returned to Earth for further study. There are also proposed missions to Titan, such as NASA's Dragonfly drone, which will explore its methane lakes and examine the possibility of exotic life forms. The discovery of extraterrestrial life, whether microbial or more complex, would be one of the most profound discoveries in human history. It would confirm that life is not unique to Earth and that the universe is teeming with possibilities. If we find even the simplest microbes on another world, it would suggest that life is likely common throughout the cosmos, given the vast number of exoplanets orbiting other stars. A single discovery within our solar system would imply that countless other planets could also harbor life. However, despite the potential for life in these places, we have yet to detect any definitive signs. This raises one of the greatest questions in modern science. If life exists beyond Earth, why haven't we seen aliens yet? This question, often referred to as the Fermi Paradox, challenges our assumptions about intelligent life in the universe. If microbial life is relatively common, could intelligent civilizations also be widespread? And if so, where are they? There are many possible explanations for this paradox. It is possible that intelligent civilizations are extremely rare and that most life in the universe remains at a microbial level. Perhaps intelligent life exists, but does not communicate in a way that we can detect. Some theories suggest that civilizations may self-destruct before they can establish interstellar contact, or that advanced beings choose to remain hidden. Another possibility is that we are simply looking in the wrong places or using the wrong methods to search for signals from alien civilizations. Regardless of these uncertainties, the search for life remains one of the most exciting endeavors in modern science. With every new mission, we come closer to answering the question of whether we are alone in the universe. The discovery of even the simplest life forms beyond Earth would revolutionize our understanding of biology and our place in the cosmos. As we continue to explore our solar system and beyond, we must prepare for the possibility that life, if it exists, may not be what we expect. The conditions required for life may be far more diverse than we currently understand. Whether life exists beneath the icy crust of Europa, within the methane lakes of Titan, or hidden in the depths of Mars, the search for extraterrestrial organisms is just beginning. The implications of such a discovery would be profound, reshaping not only our scientific understanding, but also our philosophical perspective on life and the universe itself. The question of whether we are alone in the universe has intrigued humanity for centuries. Given the vastness of space and the sheer number of potentially habitable planets, it would seem logical that intelligent life should be widespread. Yet, despite decades of searching, we have found no definitive evidence of extraterrestrial civilizations. This contradiction between the high probability of alien life and the apparent lack of contact is known as the Fermi Paradox. It challenges our understanding of life, intelligence, and the fate of civilizations across the cosmos. If the universe is filled with billions of stars, many of which have planets in the habitable zone, why haven't we seen clear signs of extraterrestrial life? One of the simplest explanations is that we might be alone. While microbial life may be common, intelligent civilizations could be extremely rare. The conditions necessary for life to emerge might be strict, requiring a perfect combination of planetary stability, the right atmospheric conditions, and a long period of uninterrupted evolution. Even if microbial life exists elsewhere, the jump from simple organisms to intelligent beings capable of developing technology may be an exceptionally rare event. On Earth, life arose relatively early in the planet's history, but it took billions of years for intelligent life to appear. If complex life requires an unusual set of circumstances, then perhaps the development of civilizations like ours is the exception rather than the rule. Another possibility is that extraterrestrial civilizations exist, but choose to remain silent. Some scientists propose that advanced species may deliberately avoid making contact, fearing potential risks. Just as human cultures throughout history have sometimes avoided contact with unknown groups for fear of conflict, alien civilizations may have reached a similar conclusion. This idea is sometimes called the zoo hypothesis, suggesting that advanced extraterrestrial beings observe us from a distance, much like zookeepers watching animals in an enclosure. If an intelligent civilization perceives us as primitive, they may choose to study us without interfering, ensuring that we develop naturally without external influence. Another possibility is that aliens are using forms of communication that we are unable to detect. Our current efforts to find extraterrestrial signals rely on detecting radio waves, but advanced civilizations may have moved beyond radio technology long ago. If an alien species developed highly sophisticated communication methods, such as quantum entanglement or exotic energy transmissions, we might be incapable of perceiving their signals. Just as an ancient civilization using smoke signals would be unable to detect modern internet transmissions, we may be technologically incapable of recognizing alien communication. A more unsettling explanation for the Fermi Paradox is the concept of the Great Filter, a theoretical barrier that prevents civilizations from advancing beyond a certain stage. The Great Filter could exist at any point in the evolutionary timeline, either preventing life from emerging, stopping intelligence from developing, or causing civilizations to self-destruct before they can spread through the galaxy. If the Great Filter occurs early, then the emergence of intelligent life might be extraordinarily rare, meaning we are one of the few, or only, advanced species in existence. If the filter is ahead of us, however, it could mean that civilizations tend to destroy themselves through war, environmental collapse, or uncontrolled technological advancements before achieving interstellar travel. The implications of each of these possibilities are profound. If we are alone, it would mean that intelligent life is an incredibly rare and fragile phenomenon, making our existence even more significant. If aliens are deliberately hiding, it suggests that advanced civilizations have a reason to remain silent. Perhaps they have learned lessons about cosmic survival that we do not yet understand. And if the Great Filter lies ahead of us, it would mean that civilizations tend to reach a certain level of development before meeting their demise. This would serve as a warning that humanity must be cautious about how we manage our technological and environmental future. Some researchers suggest that we may have already received signals from extraterrestrial civilizations, but have failed to recognize or interpret them. Throughout history, there have been numerous mysterious astronomical signals that some have speculated could be of alien origin. One of the most famous is the WOW signal, detected in 1977 by the Big Ear radio telescope. This unusual signal lasted for 72 seconds and bore characteristics expected from an artificial transmission, but it was never detected again, leaving its origin unknown. Similarly, there have been reports of unexplained fast radio bursts, intense pulses of radio energy from deep space. While these are likely natural phenomena, they demonstrate how much we still have to learn about the universe. The idea that extraterrestrial civilizations might already be sending signals is one reason why projects like SETI, Search for Extraterrestrial Intelligence, continue to scan the cosmos for signs of life. SETI researchers use massive radio telescopes to listen for potential alien transmissions, hoping to detect patterns that differ from natural cosmic noise. While no confirmed signals have been found, the search is still in its early stages compared to the vast scale of the universe. Given that our galaxy alone contains hundreds of billions of stars, it may take decades or even centuries to scan a significant portion of the sky. Some scientists argue that we should not only listen for signals, but also actively send them. This idea, known as METI, Messaging Extraterrestrial Intelligence, proposes that we should broadcast powerful messages into space, hoping that an advanced civilization will detect them and respond. However, this approach is controversial. Some researchers caution that deliberately announcing our presence to the universe could be risky, as we have no way of knowing whether an alien civilization would be friendly or hostile. While some argue that any highly advanced species would likely be peaceful, others warn that contact with an unknown civilization could be unpredictable and potentially dangerous. Another possibility is that intelligent civilizations tend to remain within their own planetary systems rather than colonizing the galaxy. Many people assume that if a civilization becomes highly advanced, it would inevitably expand outward and establish colonies on other planets. However, this might not be the case. A highly advanced civilization might have little need for expansion if it has developed technologies that allow it to meet all its needs without leaving its home system. With advanced artificial intelligence, virtual reality, and energy harvesting technologies, a civilization could potentially achieve a high standard of living without the need for interstellar travel. Alternatively, it is possible that many civilizations have risen and fallen throughout the history of the universe, but have left little trace behind. Just as ancient human civilizations have been lost to time, extraterrestrial civilizations could have emerged, developed technology, and eventually declined before we had the chance to detect them. If an alien species existed millions or even billions of years ago, the remnants of their technology could have long since vanished, leaving no evidence of their existence. Despite the uncertainty surrounding the Fermi Paradox, one thing is clear: the search for extraterrestrial life remains one of the most profound scientific endeavors of our time. Whether we are alone or not, the question of intelligent life beyond Earth challenges us to explore, innovate, and expand our understanding of the cosmos. Every new discovery, whether it is an exoplanet in a habitable zone, a strange radio signal, or new insights into the conditions necessary for life, brings us closer to answering one of humanity's oldest and most important questions. Are we truly alone in the universe? As we continue our search, we must remain open to all possibilities. If we do find evidence of extraterrestrial life, whether microbial or intelligent, it will fundamentally reshape our understanding of our place in the cosmos. If we do not, it will serve as a reminder of just how unique and precious our existence may be. Either way, the search for life beyond Earth will continue to push the boundaries of science, philosophy, and human curiosity, driving us to explore the unknown. The WOW signal remains one of the most intriguing mysteries in the search for extraterrestrial intelligence. On August 15, 1977, astronomer Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope when he noticed an unusual 72-second signal coming from the direction of the Sagittarius constellation. The signal was so strong and unexpected that he circled it on the data printout and wrote the word "wow" beside it, giving it the name it is known by today. Unlike the typical background noise detected by radio telescopes, the "wow" signal had the hallmarks of an artificial transmission, coming in at the precise frequency that hydrogen atoms naturally emit, a frequency some scientists believe extraterrestrials might use for communication. Despite efforts to find the signal again, it has never been detected a second time, leaving its true origin a mystery. Many theories have been proposed to explain the "wow" signal. Some suggest it was caused by an unknown astronomical phenomenon, while others believe it could have been interference from a satellite or a reflection of Earth-based signals. However, no conclusive explanation has ever been found. Unlike other forms of radio noise, the "wow" signal did not repeat, making it difficult to study further. If it was indeed an alien transmission, it is possible that it was a one-time message sent in our direction, or that the civilization responsible no longer exists. The possibility remains that this was our first and only intercepted message from an advanced extraterrestrial civilization. The "wow" signal is not the only strange radio burst to come from space. In recent years, astronomers have detected numerous fast radio bursts, FRBs, intense, millisecond-long flashes of radio energy originating from deep space. These bursts are far more powerful than anything produced by human technology, and their sources remain largely unknown. Some FRBs appear to be one-time events, while others have been observed repeating from the same location in the sky. Scientists initially believed that these bursts might come from neutron stars or magnetars, highly dense remnants of collapsed stars with extreme magnetic fields. However, the possibility that they could be artificial signals cannot be completely ruled out. The discovery of repeating FRBs has raised new questions about their nature. If these bursts come from a natural cosmic event, why do some of them occur in a pattern that suggests intelligent coordination? One repeating FRB, named FRB 180916, appears to send bursts at regular intervals, leading to speculation that it could be caused by an alien megastructure or an advanced civilization's method of communication. While most astronomers lean toward natural explanations, the sheer power and precision of some of these bursts keep the question open. If a civilization were to use high-energy radio transmissions to send signals across the universe, FRBs might be the kind of signals we should be looking for. Beyond radio waves, some researchers suggest that extraterrestrials could use laser technology to communicate. Radio signals have limitations. They can be scattered by interstellar dust, distorted by gravitational forces, and require massive power to send over long distances. Lasers, on the other hand, can be extremely focused and travel vast distances with minimal interference. Some SETI researchers have begun searching for potential laser pulses originating from distant star systems, looking for brief flashes of light that might indicate artificial origins. The idea is that an advanced civilization could send powerful, precisely timed laser beams as a means of interstellar communication. Projects like Breakthrough Listen, a major initiative in the search for extraterrestrial intelligence, have expanded the search for alien signals beyond just radio waves. By using the world's most powerful telescopes, astronomers are scanning the skies for both radio and optical signals that might indicate the presence of an intelligent civilization. This effort has already resulted in the discovery of several unusual signals, though none have yet been confirmed as extraterrestrial in origin. The search is complicated by the fact that space is filled with natural sources of radio waves, from pulsars and quasars to interstellar magnetic fields. Distinguishing an artificial signal from cosmic noise is an immense challenge, but one that researchers continue to tackle. One reason we may not have yet detected extraterrestrial signals is that we have only just begun listening. The Milky Way alone is over 100,000 light-years across, and our radio telescopes have scanned only a tiny fraction of the sky. If alien civilizations are transmitting on frequencies different from those we are listening to, or using forms of communication beyond our current understanding, We may simply not be looking in the right place or using the right technology. The universe is vast, and detecting a single signal from a distant civilization is like finding a single grain of sand on an entire beach. Another possibility is that extraterrestrials are intentionally avoiding detection. Some theorists propose that advanced civilizations may have reasons for staying silent, either to protect themselves from potential threats or to avoid interfering with developing species like ours. This concept, known as the dark forest theory, suggests that the universe might be a dangerous place, where civilizations that reveal themselves risk being destroyed by more powerful forces. If this is the case, it would mean that intelligent life is common, but that those civilizations have learned to remain undetectable. There is also the chance that we have already detected alien signals but failed to recognize them. Some ancient civilizations on Earth created massive stone structures without the ability to leave written records, and their messages have been lost to time. Similarly, we might have already intercepted extraterrestrial signals, but lack the means to decode or understand them. Some have even speculated that early radio signals picked up in the 20th century, long before SETI, a formal scientific effort, could have been of extraterrestrial origin, but were ignored or misclassified. While the search for alien signals continues, it has already provided valuable insights into the nature of the universe. In the process of looking for extraterrestrial transmissions, scientists have made countless discoveries about pulsars, black holes, and the large-scale structure of galaxies. The effort to detect intelligent life has led to advances in radio astronomy, data analysis, and artificial intelligence, all of which contribute to our understanding of the cosmos. Even if we never find definitive proof of an alien signal, the search itself continues to push the boundaries of science and technology. Despite the mystery surrounding signals like the WOW signal and fast radio bursts, the search for extraterrestrial intelligence remains one of the most exciting scientific endeavors of our time. If we do eventually confirm the existence of an intelligent alien civilization, it would be one of the most significant discoveries in human history. It would redefine our understanding of life, intelligence, and our place in the universe. Whether we are alone or one of many civilizations scattered across the cosmos, the question of extraterrestrial life will continue to inspire curiosity and exploration for generations to come. But even if we never find signs of intelligent life, space itself remains a place of unimaginable wonders and terrifying phenomena. From black holes that consume everything in their path, to neutron stars with magnetic fields strong enough to rip apart atoms, the universe is filled with extreme and mysterious forces. While we continue searching for signs of extraterrestrial life, we must also prepare for the reality that the universe is a far more violent and unpredictable place than we can currently comprehend. Black holes are among the most mysterious and powerful objects in the universe. They are the remnants of massive stars that have reached the end of their life cycle, collapsing under their own immense gravity. When a star several times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against the force of gravity. If the star is large enough, it undergoes a catastrophic collapse, squeezing all of its mass into an incredibly small and dense point known as a singularity. This region is surrounded by an event horizon, the point beyond which nothing, not even light, can escape. The existence of black holes was first predicted by Albert Einstein's general theory of relativity, which described how extremely massive objects can warp spacetime. However, for decades, they remained purely theoretical, as their nature made them impossible to observe directly. Scientists could only infer their presence by studying how they affect nearby stars and gas clouds. Today, we have strong evidence of their existence, thanks to observations of gravitational waves, X-ray emissions from material falling into black holes, and, most notably, the first direct image of a black hole captured in 2019. One of the most bizarre aspects of black holes is what would happen if you fell into one. The process, often called spaghettification, is a direct result of the extreme gravitational forces at play. As you approach a black hole, the gravity acting on your feet would be significantly stronger than the gravity pulling on your head, assuming you're falling in feet first. This difference in gravitational pull would stretch your body like a noodle, elongating you into a thin strand of matter before you are ultimately crushed into the singularity. From an outside observer's perspective, however, you would appear to slow down and freeze at the edge of the event horizon due to the warping of time caused by intense gravity. Black holes are more than just cosmic vacuum cleaners. While they do consume matter that ventures too close, they also shape galaxies and influence the universe in ways we are only beginning to understand. Some black holes are surrounded by massive disks of gas and dust, known as accretion disks, which heat up due to friction and emit enormous amounts of radiation. These emissions can be so powerful that they create some of the brightest objects in the universe, known as quasars. Supermassive black holes at the centers of distant galaxies that shine with the energy of billions of stars. Scientists have also speculated about the more exotic properties of black holes. Some theories suggest that they could be gateways to other universes. In particular, the concept of a white hole, a hypothetical object that is the reverse of a black hole, has intrigued physicists for decades. While black holes pull in everything, white holes would theoretically eject matter and energy. Some have proposed that black holes might act as tunnels through space-time, forming what is known as a wormhole. If such wormholes exist, they could allow for faster-than-light travel, or even access to entirely different universes. However, these ideas remain purely speculative, as no evidence of white holes or traversable wormholes has ever been observed. One of the greatest achievements in modern astronomy was the first ever image of a black hole unveiled in 2019. The image, captured by the Event Horizon Telescope, EHT, showed a supermassive black hole at the center of the galaxy M87, located 55 million light-years away. The iconic picture, a glowing ring of light surrounding a dark void, was the result of an international collaboration involving radio telescopes across the globe. By linking telescopes worldwide, scientists created a virtual telescope the size of Earth itself, allowing them to resolve details otherwise impossible to see. This groundbreaking image confirmed many predictions about black holes, particularly the way light bends around them due to their immense gravitational pull. It also provided further evidence that supermassive black holes exist at the centers of many galaxies, including our own Milky Way. In fact, another image was released in 2022, this time of the black hole at the center of our own galaxy, known as Sagittarius A star. Though smaller than the one in M87, this black hole still contains millions of times the mass of the Sun and exerts a profound influence on the stars orbiting it. Despite these advancements, many mysteries about black holes remain. One of the biggest unanswered questions is what happens inside the event horizon. According to Einstein's equations, all matter that falls into a black hole is crushed into an infinitely small point, where the laws of physics as we understand them break down. This singularity presents a major problem for our current theories of gravity and quantum mechanics, as they do not yet reconcile at such extreme conditions. Some physicists believe that new laws of physics, perhaps a theory of quantum gravity, are needed to fully understand what happens inside a black hole. Another mystery is the idea of black hole evaporation, proposed by physicist Stephen Hawking. In the 1970s, Hawking theorized that black holes are not entirely black. They actually emit tiny amounts of radiation over time due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, suggests that black holes can slowly lose mass and eventually disappear. However, this process is incredibly slow for large black holes, meaning that it would take longer than the current age of the universe for a black hole the size of our Sun to evaporate completely. If Hawking radiation is real, it raises further questions. What happens to the information that falls into a black hole? Does it vanish forever, or is it somehow preserved? This puzzle, known as the black hole information paradox, remains one of the greatest unsolved problems in theoretical physics. While black holes are among the most terrifying objects in the universe, they are not necessarily rare. Scientists believe that millions of stellar mass black holes, those formed from collapsing stars, exist throughout our galaxy alone. Some are located in binary star systems, pulling matter away from a companion star and creating powerful X-ray emissions. Others wander the galaxy unseen, detectable only by their gravitational influence on nearby stars. At the same time, supermassive black holes, containing millions or even billions of times the Sun's mass, sit at the centers of most galaxies, shaping their evolution over billions of years. The more we study black holes, the more we realize they are not just cosmic anomalies, but fundamental components of the universe. They are responsible for some of the most energetic events in existence, from the violent mergers of galaxies to the formation of powerful jets that can stretch across thousands of light years. Understanding black holes is crucial to understanding the nature of space-time itself. But while black holes are among the most extreme entities in space, they are not the only ones. The universe is filled with other extreme objects, from neutron stars that can spin thousands of times per second to magnetars with magnetic fields so strong they could tear apart atoms. Some of these objects push the limits of our understanding just as much as black holes do, showing us that the cosmos is far stranger and more violent than we ever imagined. Neutron stars are among the most extreme objects in the universe. Born from the explosive deaths of massive stars, they are the remnants left behind after a supernova, an event so powerful that for a brief moment it can outshine an entire galaxy. When a massive star runs out of fuel, its core collapses under gravity, crushing atoms so intensely that protons and electrons merge into neutrons. What remains is a hyperdense sphere, typically just about 20 kilometers in diameter, but containing more mass than the Sun. This results in an object so dense that a sugar cube-sized piece of it would weigh billions of tons on Earth. The sheer density of neutron stars is beyond human comprehension. If you were to take all of humanity, every person who has ever lived, and compress them into a single sugar cube, they would still be nowhere near as dense as neutron star material. The gravity on a neutron star is immense, about 200 billion times stronger than Earth's gravity. This means that if you were to stand on its surface, a theoretical impossibility, you would be instantly crushed into a thin layer of atoms. But neutron stars are not just incredibly dense, they are also incredibly fast. Some neutron stars, known as pulsars, spin at astonishing speeds, rotating hundreds of times per second. This rapid rotation is due to the conservation of angular momentum. When a star collapses, its core shrinks dramatically, but its rotation speeds up, just like a figure skater pulling in their arms during a spin. The fastest known pulsar, PSR J1748-2446 AD, rotates at an incredible 716 times per second. That means a single point on its surface moves at nearly 1/4 the speed of light. Pulsars are unique because they emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep across space, much like a lighthouse beam sweeping across the ocean. If Earth happens to be in the path of these beams, we detect them as pulses of radio waves, which is how pulsars got their name. These pulses are so precise that some scientists have proposed using them as cosmic clocks for interstellar navigation. However, among neutron stars, the most extreme ones are known as magnetars. These are neutron stars with magnetic fields so powerful they defy comprehension. The magnetic fields of magnetars are 1,000 trillion times stronger than Earth's, making them the most magnetic objects in the universe. If a magnetar were located as far away as the Moon, its magnetic field could erase credit card data and interfere with electronics on Earth. In fact, if you were within 1,000 kilometers of a magnetar, its magnetic field would be strong enough to disrupt the very atoms in your body, breaking apart molecules and essentially disintegrating you. Magnetars are responsible for some of the most powerful bursts of energy ever detected. Occasionally, they release enormous flares of X-rays and gamma rays, bright enough to be detected from across the galaxy. One such event occurred in 2004, when a magnetar located 50,000 light-years away released an explosion so powerful that it briefly altered Earth's upper atmosphere. This energy release was equivalent to the Sun's total output over 250,000 years, all in a fraction of a second. Despite their incredible power, neutron stars are not immortal. Over time, they gradually lose energy and slow down. Some will eventually cool down and fade into darkness, while others might merge with companion stars or other neutron stars, triggering new bursts of cosmic fireworks. When two neutron stars collide, they create some of the most violent events in the universe, killer novas, which release immense gravitational waves and forge heavy elements like gold and platinum. In fact, much of the gold found on Earth likely originated from such neutron star collisions billions of years ago. While neutron stars are some of the most extreme objects in the cosmos, they are still outmatched in sheer destructive power by supernova explosions. Some stars don't just collapse quietly into neutron stars. They go out in a spectacular cataclysmic blast that reshapes entire regions of space. A supernova is one of the most powerful and destructive events in the universe. These colossal explosions mark the death of massive stars, releasing more energy in a matter of days than our sun will emit in its entire lifetime. For a brief period, a single supernova can outshine an entire galaxy, radiating as much light as billions of stars combined. The sheer force of a supernova is staggering, capable of reshaping the cosmos by scattering elements, forming neutron stars and black holes, and even triggering the birth of new stars. Supernovae occur when a massive star reaches the end of its life cycle. For millions or even billions of years, a star maintains a delicate balance between gravity pulling inward and nuclear fusion pushing outward. This fusion process creates heavier elements within the star, from hydrogen and helium to carbon, oxygen, and eventually iron. However, iron is the breaking point. Unlike lighter elements, fusing iron does not release energy. Instead, it absorbs energy, causing the star's core to collapse under its own gravity. Within seconds, the core compresses to an unimaginable density, triggering a violent explosion, a supernova. The explosion is so intense that it sends shockwaves ripping through space, ejecting vast amounts of material at speeds of thousands of kilometers per second. The force of this explosion is what creates many of the elements found in the universe, including gold, platinum, uranium, and other heavy metals. Every atom of gold in your jewelry, every bit of iron in your blood, and even the oxygen you breathe was forged in the heart of a dying star billions of years ago. Without supernovae, life as we know it would not exist. There are two main types of supernovae: core collapse and thermonuclear. Core collapse supernovae occur when a massive star, typically at least 8 times the mass of the Sun, exhausts its nuclear fuel and its core collapses. In contrast, thermonuclear supernovae occur in binary star systems, where a white dwarf siphons material from its companion star until it reaches a critical mass and detonates in a runaway fusion reaction. Some supernovae leave behind neutron stars, while others create black holes. If the core remaining after a supernova is between 1 and 3 times the mass of the Sun, it collapses into a neutron star. But if the core is more massive, gravity overwhelms everything, forming a black hole, a region of space so dense that not even light can escape. Supernovae don't just shape the universe, they can also pose a serious threat to life. If a supernova were to occur within 30 light-years of Earth, the intense radiation could strip away our planet's ozone layer, exposing us to deadly ultraviolet rays from the Sun. Some scientists believe that past supernovae may have played a role in mass extinctions on Earth. Evidence suggests that a supernova explosion around 2.5 million years ago may have contributed to the extinction of marine species. One of the closest known supernova candidates is Betelgeuse, a red supergiant star located about 640 light-years from Earth. Betelgeuse is nearing the end of its life and could explode at any time within the next 100,000 years. When it does, it will shine as bright as the full moon in the night sky, visible even during the day. Fortunately, Betelgeuse is far enough away that its explosion will not pose any danger to Earth, but it will be one of the most spectacular celestial events humanity has ever witnessed. Despite their destructive power, supernovae are also crucial for cosmic evolution. The shock waves from these explosions can trigger the formation of new stars by compressing nearby clouds of gas and dust. In a way, supernovae are both the end and the beginning. The death of one star often leads to the birth of many others. While supernovae occur at a cosmic scale, some catastrophic events originate much closer to home. The universe is full of potential threats, and one of the most immediate dangers comes from asteroids, ancient remnants of the solar system that could, at any moment, collide with Earth and change the course of history forever. A doomsday asteroid impact is one of the most terrifying natural disasters imaginable. Throughout Earth's history, asteroid impacts have shaped the planet, and one of them led to the mass extinction of the dinosaurs. The idea that a single space rock could alter life on Earth in an instant is unsettling, but how likely is it that we could experience such an event in the near future? And if an asteroid were on a collision course with Earth, would we have any way to stop it? 66 million years ago, a 10-kilometer wide asteroid struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The force of the impact was equivalent to billions of atomic bombs exploding simultaneously. Within seconds, a massive fireball engulfed the sky, sending shockwaves across the planet. The explosion triggered tsunamis, wildfires, and an enormous cloud of dust and debris that blocked out the sun for years. The loss of sunlight caused temperatures to plummet, plants to die, and the entire food chain to collapse. An estimated 75% of all species on Earth perished, including the non-avian dinosaurs. While the Chicxulub impact is the most famous, it was not the only catastrophic asteroid collision Earth has faced. Throughout its 4.5 billion year history, our planet has been bombarded by countless space rocks, some large enough to reshape landscapes and oceans. Fortunately, most asteroids in our solar system remain in stable orbits within the asteroid belt between Mars and Jupiter, but occasionally some get knocked off course and become a potential threat to Earth. NASA and other space agencies around the world closely monitor near-Earth objects, NEOs, asteroids and comets that pass within 50 million kilometers of our planet. One of the most concerning NEOs is Apophis, an asteroid roughly 370 meters wide. When Apophis was first discovered in 2004, initial calculations suggested it had a small chance of striking Earth in 2029. However, further observations have ruled out an impact, at least for now. Instead, Apophis will pass within 31,000 kilometers of Earth, closer than some satellites in orbit. If an asteroid of this size were to hit Earth, it could release energy equivalent to hundreds of nuclear bombs, devastating an entire region. Even smaller asteroids can cause catastrophic damage. In 2013, a meteor, approximately 20 meters in diameter, entered Earth's atmosphere over Chelyabinsk, Russia. The explosion, caused by the airburst of the meteor, was powerful enough to shatter windows across an entire city, injuring over 1,000 people. This event served as a stark reminder that asteroid impacts are not just a problem of the distant past. They can happen at any time. Given the potential threat, scientists are working on ways to detect, track, and even deflect hazardous asteroids. NASA's Double Asteroid Redirection Test, DART mission, launched in 2021, successfully demonstrated that an asteroid's trajectory could be altered by crashing a spacecraft into it. The test target was Dimorphos, a small moon orbiting a larger asteroid. The impact changed Dimorphos's orbit, proving that kinetic impactor technology could be a viable method of planetary defense in the future. Other proposed asteroid deflection methods include using nuclear explosions, gravitational tractors, spacecraft that use their gravity to nudge asteroids off course, and even focus solar energy to vaporize parts of an asteroid's surface. While these ideas sound like science fiction, they could one day be necessary to prevent a catastrophic impact. Despite these advancements, we are still far from being completely safe from asteroid threats. there are thousands of undiscovered asteroids, some of which could be on a collision course with Earth. A large impact event may be rare, but it is not impossible. In the vastness of space, threats can come from anywhere, and some dangers are not as obvious as an incoming asteroid. One of the greatest cosmic mysteries is something we cannot see, yet it makes up most of the universe: dark matter. Dark matter and dark energy are among the greatest enigmas of modern physics, accounting for most of the universe's composition, yet remaining invisible and undetectable by traditional means. Scientists have long been puzzled by the fact that the matter we can see, stars, planets, gas clouds and galaxies, only makes up about 15% of the universe's total mass. The rest is something unseen, something that does not emit, absorb, or reflect light: dark matter. And beyond that, another even greater mystery exists: dark energy, an unknown force that is pushing the universe apart faster and faster. If we could understand these hidden components of the cosmos, we might unlock answers about the fundamental nature of reality itself. The existence of dark matter was first suspected in the 1930s, when astronomers noticed that galaxies were spinning much faster than expected. Based on their visible mass alone, galaxies should have been tearing themselves apart, as their rotational speeds were too high for their gravitational pull to keep them intact. The only explanation was that some unseen form of mass was providing the extra gravity needed to hold galaxies together. In the 1970s, astronomer Vera Rubin provided further evidence by studying the rotation curves of spiral galaxies, confirming that some invisible substance was exerting gravitational influence. But if dark matter exists, why can't we see it? Unlike normal matter, dark matter does not interact with light or any form of electromagnetic radiation. This makes it completely undetectable using conventional telescopes. Scientists have inferred its presence only through its gravitational effects. It seems to form a vast, unseen cosmic web, binding galaxies and clusters together like an invisible scaffolding. So what exactly is dark matter made of? There are several leading theories. One idea suggests that it could be composed of weakly interacting massive particles, WIMPs. Hypothetical particles that interact only through gravity and the weak nuclear force. Another theory proposes axions, incredibly light particles that could explain some of the strange behaviors seen in quantum physics. Despite decades of searching, however, scientists have yet to directly detect any dark matter particles. Experiments deep underground, where interference from normal particles is minimized, are currently underway in the hopes of capturing even the faintest hint of dark matter's presence. While dark matter is strange, dark energy is even more baffling. Unlike dark matter, which pulls galaxies together, dark energy is pushing the universe apart. In the late 1990s, astronomers discovered that the universe's expansion is not slowing down as expected. It is actually accelerating. The force responsible for this mysterious acceleration is what we call dark energy. It is believed to make up nearly 70% of the universe, yet we know almost nothing about it. One of the most intriguing explanations for dark energy is the idea of a cosmological constant first proposed by Albert Einstein. He initially introduced the concept to maintain a static universe in his equations, but later abandoned it when Edwin Hubble proved that the universe was expanding. However, modern observations suggest that something very similar to Einstein's cosmological constant may be real, a property of space itself that causes expansion. Another possibility is that dark energy is a form of quintessence, a dynamic energy field that changes over time. If this is the case, the fate of the universe could be even more unpredictable than we currently imagine. Some theories suggest that dark energy could eventually become so powerful that it rips galaxies, stars, and even atoms apart in a scenario known as the Big Rip. Despite its mysterious nature, dark energy has been measured with remarkable precision. Observations of distant supernovae, cosmic microwave background radiation, and galaxy clusters all point to the same conclusion. Dark energy is real, and it is the dominant force shaping the fate of our universe. If we could understand dark matter and dark energy, it would revolutionize physics. Some scientists speculate that dark matter could hold the key to hidden dimensions, or even parallel universes. Others wonder if dark energy could one day be harnessed as a nearly infinite power source. But for now, these cosmic forces remain elusive. This raises an even bigger question. What if our universe itself is just a tiny part of something even greater? Could we be living in a multiverse, one of countless other universes beyond our own? The idea of a multiverse is one of the most astonishing and mind-bending concepts in modern physics. It suggests that our universe, the vast cosmos filled with countless galaxies, stars, and planets, may be just one of an infinite number of universes, each existing independently and possibly following different physical laws. If this idea is true, then everything we know, from the laws of physics to the fundamental nature of reality, could be just one small piece of an unimaginably vast cosmic structure. The multiverse concept arises from several different branches of physics and cosmology. One of the most well-known sources of the multiverse idea comes from quantum mechanics, specifically the many worlds interpretation. This theory proposes that every time a quantum event occurs with multiple possible outcomes, the universe splits into different versions, each representing a different outcome. In this view, there is a separate universe for every possible decision, every roll of a dice, and every moment in history. If this interpretation is correct, then infinite parallel universes could exist, with versions of ourselves living out every possible variation of our lives. Another major source of the multiverse hypothesis comes from cosmic inflation, the theory that explains how the universe expanded rapidly in the first fraction of a second after the Big Bang. Some versions of inflation theory suggest that different regions of space could have expanded at different rates, creating bubble universes that are completely separate from one another. Each bubble could have its own physical laws, meaning that some universes might have entirely different forces of nature, different numbers of dimensions, or even different types of matter and energy. One of the most extreme versions of the multiverse idea comes from string theory, a highly theoretical framework that attempts to unify all fundamental forces of nature. String theory suggests that there could be extra dimensions beyond the three of space and one of time that we experience. These extra dimensions could allow for an enormous number of possible universes, each with its own unique properties. Some physicists estimate that string theory allows for as many as 10 to the power of 500 different possible universes, an almost incomprehensibly large number. If the multiverse exists, it raises profound questions about the nature of reality. Are we living in just one random universe among many, or is there a deeper reason why our universe has the particular properties it does? Some scientists propose that the apparent fine-tuning of physical constants, such as the precise strength of gravity and electromagnetism, could be explained if there are countless other universes where the laws of physics are different. In this view, we simply happen to live in one of the rare universes that allow for complex structures like galaxies, stars, and life to exist. But how could we ever test the idea of a multiverse? One possibility is that if our universe has ever interacted with another universe in the past, there might be physical evidence of this interaction. Some cosmologists have suggested that subtle patterns in the cosmic microwave background radiation, the leftover heat from the Big Bang, could provide clues about collisions between bubble universes. Others have speculated that black holes might be gateways to other universes, with matter that falls into a black hole possibly emerging in another reality. The idea of black holes as portals to other universes is particularly intriguing. Some versions of Einstein's equations suggest that if a black hole were to form under the right conditions, it could create a white hole in another universe, a region where matter and energy are expelled instead of being pulled in. This idea has led some physicists to wonder if our own universe might have been born from a black hole in a parent universe. If true, this would mean that black holes in our universe could be continuously creating new universes, each with slightly different properties. Of course, the multiverse remains a highly speculative concept. Many scientists argue that without concrete evidence, it is more of a philosophical idea than a scientific one. However, even if we can never directly observe other universes, the mathematics behind the multiverse theories is compelling, and they provide a possible explanation for some of the biggest mysteries in physics. If we do live in a multiverse, it would completely change our perspective on existence. It could mean that everything we know is just one small part of an unimaginably vast cosmic landscape. It could also mean that somewhere, in some distant universe, there might be another version of you, perhaps living in a world where history unfolded differently, or where the laws of physics are not what we know them to be. Whether or not the multiverse exists, it forces us to think about the nature of reality in new and deeper ways. But even within our own universe, there is still one of the greatest mysteries of all: time itself. Time is something we experience every second of our lives, yet it behaves in ways that are completely counterintuitive. What is time? Why does it seem to flow in one direction? And could time itself be an illusion? Time is one of the most fundamental and mysterious aspects of our universe. We experience it every second of our lives, yet it behaves in ways that defy common sense. Time seems to flow in one direction, from the past to the future. But why? Could time be an illusion? And what happens when we push the limits of time itself, traveling near the speed of light or approaching a black hole? Modern physics has revealed that time is not as simple as we once thought, and the deeper we look, the stranger it becomes. At the heart of our understanding of time is Einstein's theory of relativity. Before Einstein, time was believed to be absolute, ticking at the same rate for everyone, everywhere in the universe. This idea goes back to Isaac Newton, who imagined time as a universal, unchanging flow. But Einstein shattered this notion with his groundbreaking theory of special relativity, showing that time is not fixed, but instead depends on speed and gravity. One of the key concepts in Einstein's theory is time dilation. According to special relativity, time moves slower for objects that travel at high speeds. The faster you move, the slower your clock ticks compared to someone at rest. This effect is not just theoretical, it has been confirmed through experiments. For example, atomic clocks placed on high-speed jets have been shown to tick slightly slower than identical clocks on the ground. Perhaps the most extreme example of time dilation occurs near black holes. According to Einstein's general theory of relativity, gravity also affects time. The stronger the gravitational field, the slower time moves. If you were to approach a black hole, an observer watching from a safe distance would see your movements slow down dramatically. In fact, if you got close enough, time for you would nearly freeze relative to the outside universe. This means that a person falling into a black hole would never be seen crossing the event horizon. They would appear frozen in time at the edge. But if time is relative, does that mean time travel is possible? In some ways, we are already time travelers. Every second, we are all moving forward in time. And because of time dilation, astronauts who spend extended periods in space age slightly less than those of us on Earth. This means that if a person were to travel near the speed of light and then return to Earth, they would find that much more time had passed here than for them. This concept, known as the twin paradox, has been tested with precise atomic clocks. The idea of traveling backward in time, however, is far more controversial. Some solutions in Einstein's equations suggest that time travel to the past could be possible through wormholes, hypothetical tunnels in space-time that connect distant points. If a wormhole could be stabilized, it might allow someone to enter at one end and emerge at the other at an earlier time. However, wormholes are purely theoretical, and many physicists believe they would be too unstable to allow actual time travel. Another theoretical way to travel through time is by using cosmic strings, extremely thin but incredibly dense structures that may have formed in the early universe. Some scientists suggest that if two cosmic strings were to pass close to each other, they could warp spacetime in such a way that a closed time loop could form. But like wormholes, cosmic strings remain purely hypothetical, and there is no evidence that they actually exist. One of the biggest mysteries about time is why it moves in only one direction. In physics, most fundamental equations work the same, whether time moves forward or backward. But in reality, we always experience time moving from the past to the future. The reason for this may lie in a concept called entropy. Entropy is a measure of disorder in a system, and according to the second law of thermodynamics, entropy always increases over time. This means that the universe moves from order to disorder, giving time its apparent direction. But could time itself be an illusion? Some physicists believe that time is not a fundamental property of the universe, but instead emerges from deeper, more fundamental laws of physics. In certain theories, time may not even exist at the most fundamental level of reality. Instead, what we perceive as time might be an emergent property of the way the universe works on a larger scale. The nature of time is closely linked to the ultimate fate of the universe. If the universe continues expanding forever, time will continue flowing forward. But if the universe were to collapse in a big crunch, some theories suggest that time could reverse. Another possibility is that time itself could eventually stop making sense if the universe becomes so empty and cold that no meaningful changes can occur. Time is one of the deepest mysteries in physics, and our understanding of it is still evolving. Whether time is an absolute reality or an emergent property, it shapes every aspect of our existence. It determines how we experience the world, governs the laws of physics, and may even hold the key to understanding the ultimate nature of reality. But even as we uncover the secrets of time, we must also consider how time shapes the biggest question of all. What will happen to the universe in the end? The end of the universe is one of the most profound questions in cosmology. Will everything we know fade into darkness? Will the fabric of space itself be torn apart? Or could the universe cycle through endless rebirths, repeating its history over and over again? Scientists have spent decades studying the fate of the cosmos, using mathematical models, observations, and our best understanding of physics to predict how it might all come to an end. While we don't yet know the definitive answer, several leading theories paint a picture of what the distant future of our universe could look like. One of the most widely accepted scenarios is known as the Big Freeze, also referred to as the heat death of the universe. This theory is based on our current understanding of dark energy, the mysterious force driving the accelerating expansion of the universe. Right now, galaxies are moving away from each other at ever-increasing speeds, and if this expansion continues indefinitely, the universe will eventually become a vast, cold, and empty place. As time progresses, stars will burn through their nuclear fuel and die. The largest stars will explode in supernovae, leaving behind neutron stars and black holes, while smaller stars will simply fade into cold remnants. Over trillions of years, new star formation will slow down until no new stars are born. Without stars, galaxies will go dark, leaving only black holes and frozen, dead planets drifting through space. Even black holes will eventually evaporate due to a process called Hawking radiation, releasing their mass as faint, slow-burning energy until nothing remains but a thin mist of elementary particles, spread so far apart that no meaningful interaction can take place. The universe, once teeming with energy and matter, will become a void, cold, silent, and devoid of life. But what if the universe doesn't expand forever? Some theories propose the opposite fate, the Big Crunch. In this scenario, the expansion of the universe would eventually slow down and reverse, causing everything to collapse back into a singularity. This idea was originally more popular before the discovery of dark energy, as scientists expected gravity to slow and eventually stop the expansion. If dark energy were to weaken or reverse in strength, the attractive force of gravity could once again dominate, pulling galaxies back together. As the universe shrinks, temperatures would rise, galaxies would merge, and eventually, all matter would be compressed into an unimaginably dense and hot state. In the final moments before the collapse, the entire universe would exist as an ultra-hot plasma, similar to its state just after the Big Bang. If this happens, the universe would essentially end in a fiery, chaotic implosion, the opposite of the Big Bang that created it. But what happens after? Some physicists propose that the universe could then bounce back in a new Big Bang, beginning the cycle all over again, a concept known as the cyclic universe. Another possibility is the Big Rip, a much more violent and unsettling fate. This scenario is based on the idea that dark energy is not just pushing galaxies apart, but is also increasing in strength over time. If dark energy continues to grow stronger, it could eventually reach a point where it overcomes all other fundamental forces. At first, galaxies would drift so far apart that they would no longer be able to interact. Then, dark energy would tear apart galaxies themselves, then solar systems, and eventually even planets. In the final moments of the Big Rip, the force would become so extreme that it would tear apart atoms themselves, destroying the very fabric of space-time. If this is our fate, the universe will not die slowly. It will be ripped apart in a cataclysmic event where everything, down to the smallest subatomic particles, is obliterated. But could there be another way? Some physicists propose that the universe may not have a definitive end, but rather go through endless cycles of expansion and contraction. This idea, known as the cyclic universe, suggests that after a big crunch, a new Big Bang could occur, resetting the universe and starting the cycle anew. There are even some theories that propose the remnants of a previous universe could influence the properties of the next, meaning that patterns, structures, or even information could be carried forward from one universe to another. If this idea is true, it would mean that the universe has no beginning or end, just an eternal cycle of birth, death, and rebirth. Another intriguing idea is the concept of a quantum bounce, proposed in certain versions of quantum gravity. According to this theory, the extreme density of a collapsing universe would create quantum effects that prevent a true singularity from forming. Instead, a new expansion phase would emerge, allowing the universe to be reborn in an endless cycle. While this idea is still highly speculative, it offers an alternative to both eternal expansion and total destruction. Even more exotic possibilities exist, such as the idea that our universe could be absorbed into a larger structure. Some theories propose that our universe is part of a larger multiverse, where new universes are constantly being born and dying. If this is the case, the end of our universe may simply mean its transition into a different state, possibly merging with another universe or spawning new ones in the process. No matter which scenario turns out to be correct, one thing is certain: the universe is changing, and its ultimate fate will be determined by the forces that govern it. Whether it ends in a slow freeze, a violent crunch, a cosmic rip, or an endless cycle, the fate of the universe is a mystery that scientists continue to explore. But before we can fully understand the end, we must go back to the beginning. How did everything come into existence? What forces set the cosmos into motion? The answer to these questions takes us back over 13 billion years to the very first moments of time itself. The Big Bang is often described as the moment when everything, space, time, matter, and energy, came into existence. But what exactly does that mean? How did something as vast as our universe emerge from what appears to be nothing? And what was there before the Big Bang? These are some of the most profound questions in cosmology, and while scientists have uncovered incredible details about the universe's earliest moments, many mysteries remain. The term Big Bang can be misleading because it suggests an explosion in space. In reality, the Big Bang was not an explosion in space. It was the rapid expansion of space itself. The universe didn't expand into an empty void. Rather, space itself stretched and grew, carrying matter and energy with it. This expansion continues even today, with galaxies moving apart as the fabric of space itself stretches. The story of our universe begins approximately 13.8 billion years ago. At this moment, everything we see today, the galaxies, stars, planets, and even the particles that make up our bodies, was compressed into an incomprehensibly small and dense state. Scientists refer to this as a singularity, a point where the laws of physics as we know them break down. In this state, temperatures and energy levels were unimaginably high. and space-time itself was warped beyond recognition. The first fraction of a second after the Big Bang was dominated by a period known as cosmic inflation. During this time, the universe expanded exponentially, growing from a size smaller than an atom to a vast region in an almost unimaginably short amount of time. This inflationary phase helped explain why the universe appears so uniform today, why galaxies are spread relatively evenly throughout space, and why the cosmic microwave background radiation, the leftover heat from the Big Bang, appears nearly the same in all directions. As inflation slowed, the universe continued to expand, but at a more gradual rate. At this point, temperatures were still extreme, but they began to cool just enough for fundamental forces to separate. The four fundamental forces that govern the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, each emerged in this early stage, setting the foundation for all physical interactions that would come later. In the first few minutes after the Big Bang, a process called nucleosynthesis took place. This was when the first atomic nuclei were formed, primarily hydrogen and helium, along with tiny traces of lithium. These elements would later become the building blocks of stars, galaxies, and eventually life itself. However, for a long time, the universe remained an extremely hot, dense plasma, a chaotic soup of charged particles that could not yet form stable atoms. As the universe continued to expand and cool, something remarkable happened. Around 380,000 years after the Big Bang, for the first time, temperatures dropped low enough for electrons to combine with nuclei, forming neutral atoms. This event is known as recombination, and it allowed photons, particles of light, to travel freely through space for the first time. The light released during this period is what we now observe as the cosmic microwave background radiation, a faint glow that still exists in all directions, serving as a fingerprint of the universe's early history. With neutral atoms now forming, the universe became transparent, and matter began to clump together under the influence of gravity. However, it would take hundreds of millions of years before the first stars and galaxies emerged. During this period, often called the Cosmic Dark Ages, the universe was mostly filled with neutral hydrogen gas, with no sources of visible light, but gravity was working behind the scenes, pulling matter together to form the first cosmic structures. Eventually, around 100 million to 200 million years after the Big Bang, the first stars were born. These early stars were enormous, much larger than the stars we see today, and they burned through their fuel quickly. They played a crucial role in shaping the universe, as their intense radiation began to ionize the surrounding hydrogen, ending the cosmic dark ages and ushering in an era of light known as cosmic reionization. These first stars also set the stage for the formation of galaxies. Over hundreds of millions of years, gravity continued to pull matter together, forming larger and more complex structures. Some of these early galaxies would eventually merge to create even larger galaxies, including our own Milky Way. One of the biggest questions in cosmology is whether anything existed before the Big Bang. If the Big Bang was the beginning of everything, then what came before? The truth is, we don't know for sure. Some theories suggest that our universe is just one in an infinite cycle of expansion and contraction, meaning that a previous universe may have existed before ours. This idea aligns with the cyclic universe theory, which proposes that the universe undergoes endless cycles of big bangs and big crunches. Another possibility is that our universe was born from a quantum fluctuation in a larger multiverse. Some models suggest that what we call the Big Bang could have been a localized event, with countless other universes existing beyond our own. In this view, our universe may have simply emerged as a small pocket of reality within an even greater cosmic landscape. There are also theories based on quantum mechanics that suggest space-time itself is not fundamental, but emerges from a deeper, more complex reality. Some scientists speculate that the fabric of reality could be connected to strange quantum phenomena, meaning that the true nature of existence may be beyond anything we currently understand. Despite all these possibilities, The one thing we know for certain is that the Big Bang marked the beginning of the universe as we perceive it. It set everything in motion: the formation of atoms, the birth of stars, the creation of galaxies, and eventually the emergence of life. But while the early universe was chaotic and violent, over time it gave rise to order. The forces of nature shaped the cosmos, allowing structures to form and evolve. Planets would eventually emerge, some of which would develop the right conditions to support life. And among them, one small, rocky world orbiting an ordinary star in the outskirts of the Milky Way would become home to beings capable of pondering their own origins. The story of the universe is far from over. In fact, we are still in the midst of an incredible journey, witnessing the universe as it continues to evolve, from the fiery birth of the cosmos to the formation of galaxies and planets. Everything we see today is a result of billions of years of cosmic history. But the early universe looked nothing like the one we live in today. In the next chapter of our journey, we will explore how the first galaxies and stars changed the universe, paving the way for everything we know to exist. The birth of the first stars and galaxies was one of the most transformative periods in the history of the universe. After the Big Bang, the cosmos was an expanding, searing hot sea of energy and fundamental particles. Over time, it began to cool, allowing matter to form stable structures. However, the universe remained in darkness for millions of years. There were no stars, no galaxies, only vast clouds of hydrogen and helium drifting through space. This period, known as the Cosmic Dark Ages, persisted until the first stars ignited, flooding the universe with light for the first time. These first stars, known as Population 3 stars, were unlike any that exist today. They were composed almost entirely of hydrogen and helium, as heavier elements had not yet been forged in the nuclear furnaces of stellar cores. Because they lacked elements like carbon, oxygen, and iron, these stars behaved differently from modern ones. Theoretically, they could have reached enormous sizes, hundreds of times the mass of the Sun, and burned through their fuel at an incredible rate. Unlike long-lived stars such as our Sun, these ancient behemoths lived for only a few million years before dying in violent supernova explosions. When these first stars exploded, they released heavy elements into space, enriching the surrounding gas clouds. This process was crucial as it allowed future generations of stars to form with elements that would later give rise to planets and life. The remnants of these stellar explosions also played a key role in triggering the collapse of nearby gas clouds, leading to the formation of more stars. Over time, gravity pulled these newly forming stars together into clusters, which merged into the first primitive galaxies. The formation of galaxies marked the next major stage in the evolution of the universe. The earliest galaxies were chaotic, irregularly shaped structures filled with young, hot stars. Unlike the grand spiral and elliptical galaxies we see today, these early galaxies were constantly colliding and merging, reshaping themselves over billions of years. As more stars formed, their radiation began to ionize the surrounding gas, stripping electrons from hydrogen atoms. This process, known as the era of reionization, occurred roughly 1 billion years after the Big Bang and had a profound effect on the universe. It cleared away the neutral hydrogen that had previously absorbed light, allowing the cosmos to become transparent. One of the most important pieces of evidence for this early phase of the universe is the cosmic microwave background, or CMB. This faint radiation is the oldest light we can see, a relic from the time when the universe first became transparent. It was discovered in the 1960s by accident, when scientists detected a persistent radio signal that seemed to come from all directions. What they had stumbled upon was the afterglow of the Big Bang itself, a snapshot of the universe when it was only 380,000 years old. The cosmic microwave background provides astronomers with a unique window into the early universe. By analyzing its tiny temperature variations, scientists can learn about the distribution of matter, the overall shape of the cosmos, and the conditions that led to the formation of the first galaxies. It also offers critical clues about the nature of dark matter and dark energy. two of the biggest mysteries in modern astrophysics. Despite its significance, the CMB only tells part of the story. To truly understand how the first galaxies formed, astronomers need to look even further into the past. This is where telescopes like the James Webb Space Telescope come into play. Unlike traditional optical telescopes, which can only observe visible light, James Webb is designed to detect infrared light. This allows it to see through thick clouds of dust and gas, revealing objects that were previously hidden from view. Because light takes time to travel across the universe, looking at distant galaxies means looking back in time. By studying galaxies that are billions of light years away, astronomers can witness the universe as it was billions of years ago. James Webb's powerful instruments have already provided breathtaking images of galaxies that existed just a few 100 million years after the Big Bang, giving us an unprecedented look at the universe's infancy. One of the major questions astronomers hope to answer is how galaxies grew and evolved over cosmic time. The earliest galaxies were small and irregularly shaped, but over billions of years, they merged and collided to form the vast, structured galaxies we see today. The Milky Way itself is the product of many such mergers, and even now, it continues to consume smaller galaxies in its vicinity. In about 4 billion years, it is expected to collide with the Andromeda Galaxy, creating an entirely new galactic structure. Another mystery that telescopes like James Webb are helping to solve is the role of supermassive black holes in galaxy formation. Nearly every large galaxy, including our own, has a supermassive black hole at its center. These black holes can be millions or even billions of times the mass of the Sun, and their immense gravitational pull influences the movement of stars and gas within their galaxies. Some of these black holes are extremely active, consuming enormous amounts of matter and producing powerful jets of energy that can shape the surrounding galaxy. The study of these early galaxies is not just about understanding the past, it is also about uncovering the fundamental rules that govern the universe. By piecing together the history of star formation, galaxy evolution, and cosmic structure, scientists can refine their models of how the universe works. Each discovery brings us closer to answering some of the biggest questions in cosmology. How did the first structures form? What role did dark matter and dark energy play? And ultimately, what does this tell us about the future of the universe? As we continue to push the boundaries of observational astronomy, new discoveries are constantly reshaping our understanding of the cosmos. The early universe was a place of rapid transformation, where tiny fluctuations in the density of matter eventually led to the vast and complex structures we see today. And yet, despite all that we have learnt, there is still so much we do not know. The search for the first stars and galaxies is not just a scientific endeavour. It is a journey to understand our own cosmic origins. Every atom in our bodies was forged in the heart of ancient stars, and every galaxy we see is part of a vast, interconnected web stretching across the cosmos. By looking deeper into space, we are also looking deeper into our past, uncovering the story of how everything came to be. And yet, not all galaxies fit neatly into our models. Some defy expectations, challenging our assumptions about how the universe should behave. The next step in our journey takes us to some of the strangest galaxies ever discovered, places where the laws of physics seem to bend and where new mysteries await. Galaxies are the fundamental building blocks of the universe, vast collections of stars, gas, dust, and dark matter bound together by gravity. While many galaxies follow familiar patterns, spirals, ellipticals, and irregular shapes, some defy all expectations, challenging our understanding of cosmic evolution. These galaxies exhibit unusual structures, immense sizes, or mysterious behaviors that hint at forces we do not yet fully comprehend. From peculiar ring-shaped formations to the largest galactic giants ever discovered, the strangest galaxies in the universe continue to astonish astronomers. One of the most fascinating examples of an unusual galaxy is Hoag's object. At first glance, it appears to be a nearly perfect ring of stars encircling a central core, but this structure is unlike anything typically seen in spiral or elliptical galaxies. The outer ring, composed of young, hot blue stars, is completely detached from the older, yellowish stars in the central region. The origin of this bizarre formation remains a mystery. One possibility is that Hoag's object was once a normal galaxy that experienced a catastrophic collision with another galaxy, stripping away its outer layers and leaving only the dense core. Another theory suggests that gravitational interactions between Hoag's object and another cosmic body could have shaped the ring-like structure over time. What makes it even stranger is that a nearly identical ring-shaped galaxy can be seen in the background of images taken of Hoag's object, suggesting that such formations might not be as rare as we once believed. While Hoag's object is strange because of its shape, IC1101 is remarkable for its sheer size. It is the largest known galaxy in the observable universe, stretching an astonishing 6 million light-years across, more than 60 times the diameter of the Milky Way. IC1101 is an enormous elliptical galaxy located in the center of the Abell 2029 galaxy cluster. Unlike spiral galaxies, which have well-defined arms and abundant star formation, elliptical galaxies like IC1101 are often composed of older stars and contain little gas or dust to fuel new star formation. Over billions of years, IC1101 has likely grown through countless mergers with smaller galaxies, gradually accumulating its immense mass. At its core lies a supermassive black hole, one of the largest ever detected, exerting a powerful influence on the surrounding stars. If a civilization existed on a planet within IC1101, their night sky would be filled with an overwhelming number of stars, densely packed together, creating a cosmic vista unlike anything seen from Earth. Beyond individual galaxies, entire galactic systems are shaped by interactions that unfold over billions of years. Galaxies do not exist in isolation. Gravity continuously pulls them toward one another, and over time, they can collide and merge in spectacular cosmic events. Contrary to what one might expect, when galaxies collide, their stars do not necessarily smash into each other. The vast distances between individual stars mean that direct collisions are rare. Instead, the gravitational forces between the merging galaxies trigger massive waves of star formation, reshaping their structures and giving rise to entirely new formations. One of the most well-known examples of this process is the collision between the Milky Way and the Andromeda Galaxy, which is expected to occur in about 4 billion years. As these two massive galaxies interact, they will likely merge into a single, even larger galaxy, sometimes referred to as Milkomeda. Such galactic mergers are common throughout the universe, playing a crucial role in shaping the structure of the cosmos. One of the great mysteries surrounding galaxies is their rotation. Observations show that the outer regions of galaxies rotate much faster than expected, based on the visible matter they contain. According to the laws of physics, the gravitational pull from the galaxy's stars and gas alone should not be enough to hold these rapidly moving outer stars in place, yet they do not fly apart. This strange behavior suggests that there is an unseen mass providing additional gravitational pull, a phenomenon attributed to dark matter. Dark matter is thought to make up about 85% of the universe's total mass, yet it does not emit, absorb, or reflect light, making it invisible to our telescopes. Scientists infer its existence based on its gravitational effects on galaxies and galaxy clusters. If dark matter did not exist, galaxies as we know them would not be able to maintain their structures, and the universe would look very different from what we observe today. Some galaxies, known as ultra-diffuse galaxies, challenge even our current understanding of dark matter. These galaxies appear to contain far less dark matter than expected, leading to speculation about whether they formed differently or if dark matter itself behaves in ways we do not yet understand. Others, like the so-called dark galaxies, are almost entirely composed of dark matter with very few visible stars, adding yet another layer of mystery to the study of galactic structures. Despite the strange and diverse galaxies we have already discovered, there are likely countless more bizarre and unexplained structures waiting to be found. With advancements in telescope technology, such as the James Webb Space Telescope and future observatories, we are continuously pushing the boundaries of our knowledge, revealing new and unexpected details about the cosmos. The nature of galaxies remains one of the most compelling areas of study in modern astrophysics. Some galaxies grow into massive elliptical giants, while others remain small and faint, barely visible against the backdrop of the universe. Some are torn apart by gravitational forces, while others mysteriously hold together against all odds. Each discovery brings new insights, yet also raises new questions, reminding us that our understanding of the cosmos is still incomplete. But even as we study galaxies, a larger question looms. Could all galaxies, including the Milky Way, be moving inside an even larger cosmic structure? Observations of the large-scale distribution of galaxies suggest that they are not randomly scattered across the universe, but instead arranged in vast cosmic webs of filaments, walls, and voids. This raises the possibility that our entire galaxy, and everything within it, is part of a far greater cosmic design, one that we are only beginning to comprehend. The universe, at first glance, appears to be an endless and chaotic expanse filled with galaxies scattered randomly across space. However, when we observe the cosmos on the largest possible scales, an incredible pattern begins to emerge, one that reveals the universe is anything but random. Galaxies are not evenly spread out. Instead, they are woven together in a vast, interconnected structure known as the cosmic web. This immense network of filaments, clusters, and voids is the true underlying architecture of the universe, shaping the very fabric of existence. The cosmic web is the result of billions of years of gravitational interactions between dark matter, ordinary matter, and the energy that fills the universe. In the earliest moments after the Big Bang, the universe was nearly uniform, with only slight variations in density. Over time, gravity amplified these tiny variations, pulling matter together into dense regions, while empty spaces grew larger. The result was the formation of long, thread-like filaments made up of galaxies, gas, and dark matter stretching across billions of light years. These filaments intersect at enormous nodes called galaxy superclusters, where thousands of galaxies are packed together. Meanwhile, the spaces between these filaments, known as cosmic voids, are vast, nearly empty regions spanning hundreds of millions of light years, with very few galaxies inside them. The cosmic web is best visualized through large-scale surveys of the universe, such as the Sloan Digital Sky Survey, which maps the positions of millions of galaxies. When plotted in 3 dimensions, the distribution of galaxies reveals a structure strikingly similar to neural networks in the human brain, or even the filaments of a living organism. Some researchers have even speculated that the cosmic web might share fundamental similarities with biological systems, leading to intriguing philosophical questions about the nature of the universe itself. Could the cosmos be, in some way, alive? While this idea remains purely speculative, the resemblance between the cosmic web and biological structures is a fascinating mystery that continues to inspire new research. One of the most astonishing aspects of the cosmic web is the presence of superstructures, regions of the universe where matter is concentrated on an immense scale. The largest of these is the Hercules Corona Borealis Great Wall, an enormous filament of galaxies stretching over 10 billion light-years across. Discovered in 2013, this structure challenges our understanding of cosmic evolution, as its size is so vast that it defies the standard models of how the universe should be organized. According to our current theories, gravity should not have had enough time to form such an enormous structure within the universe's 13.8 billion year lifespan. The existence of the Hercules Corona Borealis Great Wall suggests that our understanding of large-scale cosmic structures may still be incomplete, hinting at new physics or hidden forces shaping the cosmos in ways we do not yet comprehend. Another mind-boggling structure is the Baryon Oscillation Spectroscopic Survey, BOSS, Great Wall, which spans roughly 1 billion light-years. This massive collection of galaxy clusters is so large that some astronomers question whether it should even be considered a single structure or merely a coincidence of neighboring clusters. The boundaries between different cosmic structures remain an open question, as the universe does not have clearly defined edges or divisions. Instead, everything is connected through an intricate web of gravity and matter, stretching across the void of space. The cosmic web also plays a crucial role in the movement of galaxies. Recent studies suggest that galaxies within filaments and superclusters are not stationary. They flow along the web's structures, moving toward regions of higher density due to the pull of gravity. This motion is influenced by unseen forces, including dark matter, which is thought to provide the additional gravitational pull necessary to maintain the web's structure. The mysterious behavior of dark matter is still one of the biggest challenges in modern astrophysics, and understanding its role in shaping the cosmic web may provide crucial insights into the fundamental nature of the universe. Interestingly, our own galaxy, the Milky Way, is part of this grand cosmic tapestry. It resides within the Laniakea supercluster, a vast collection of galaxies spanning over 500 million light-years. Within Laniakea, the Milky Way is being drawn toward a gravitational anomaly known as the Great Attractor, a dense region of space whose exact nature remains unclear. The Great Attractor exerts a powerful pull on our galaxy, along with thousands of others, suggesting that there is an enormous concentration of mass hidden within this region. Some scientists believe that this unseen mass may be due to dark matter or even an undiscovered supermassive structure within the cosmic web. Despite our growing understanding of the cosmic web, many questions remain unanswered. How did such immense structures form in the first place? Are there even larger structures beyond our current observational limits? Could there be hidden forces or unknown physics shaping the universe on the largest scales? Future telescopes, such as the upcoming Euclid mission and the Vera C. Rubin Observatory, aim to map even greater portions of the cosmic web, potentially uncovering new surprises about the way matter is distributed throughout the cosmos. The discovery of the cosmic web has profoundly changed our perception of the universe. Rather than being a collection of isolated galaxies drifting through space, the universe is an interconnected, dynamic system where gravity, dark matter, and cosmic expansion work together to shape the cosmos. The realization that galaxies are part of an enormous organized network challenges the idea of randomness and suggests that the universe follows a set of deeper, underlying principles that we have yet to fully understand. As we continue to explore the largest scales of the universe, it becomes clear that our cosmic neighborhood is just one small piece of a much greater whole. The cosmic web stretches far beyond what we can currently observe, hinting at a universe that is even more complex and interconnected than we ever imagined. But while the study of the cosmic web helps us understand the largest structures in existence, we must not forget the mysteries much closer to home. Even our own star, the Sun, holds secrets that continue to puzzle scientists. From its violent eruptions to the enigma of its outer layers, the Sun remains one of the most fascinating and essential objects in our search for knowledge about the universe. The Sun, our life-giving star, is far more complex and mysterious than it may appear at first glance. Though it seems like an eternal, unchanging presence in the sky, the Sun is a dynamic and sometimes violent object, governed by forces we still do not fully understand. Its radiant glow sustains life on Earth, drives weather patterns, and influences the delicate balance of our climate. Yet, beneath its seemingly constant appearance lies a world of turbulence and change. While it may look like a giant ball of fire, the Sun is not actually burning in the way a fire does. Instead, it is a massive nuclear fusion reactor, constantly converting hydrogen into helium at unimaginable temperatures and pressures. This fusion process releases enormous amounts of energy, which travels outward from the Sun's core and eventually reaches Earth, making life possible. Without this continuous energy output, Earth would be an icy, lifeless world, incapable of supporting the vast array of life forms that thrive on its surface. At the Sun's heart lies its core, a region of extreme density and heat where nuclear fusion occurs. Here, temperatures soar to about 15 million degrees Celsius. The intense gravitational pressure in the core forces hydrogen atoms to collide and fuse together in a process known as nuclear fusion, creating helium and releasing energy in the form of photons. These photons take an incredibly long time, potentially thousands to millions of years, to travel from the core to the sun's surface due to the immense density of solar matter. As they make their way outward, they pass through the radiative zone, a layer where energy is transported through radiation rather than convection. Beyond this lies the convective zone, where hot plasma rises and cooler plasma sinks in a continuous churning motion, similar to the bubbling of boiling water. Eventually, the energy escapes from the sun's outermost visible layer, the photosphere, which emits the light we see. The sun's surface, known as the photosphere, is significantly cooler than its core, with temperatures of about 5,500 degrees Celsius. However, one of the sun's biggest mysteries lies above its surface, the corona, a vast outer atmosphere of superheated plasma. The corona extends millions of kilometers into space and exhibits an astonishing phenomenon. It is far hotter than the sun's surface. While common sense dictates that temperature should decrease as we move away from a heat source, the corona defies this expectation by reaching temperatures of over 1 million degrees Celsius. Scientists have long been puzzled by this anomaly, and several theories attempt to explain it. One prominent hypothesis is that magnetic waves generated by the sun's powerful magnetic field transfer energy to the corona, heating it to extreme temperatures. Another theory suggests that nanoflares, small, rapid bursts of magnetic energy, continuously inject heat into the corona. Despite decades of study, the exact mechanism remains uncertain, and ongoing solar missions like NASA's Parker Solar Probe aim to unravel this enduring mystery. The sun does not remain constant. It undergoes an approximately 11-year cycle of activity, known as the solar cycle. This cycle is driven by changes in the sun's magnetic field, which affects the number of sunspots, solar flares, and coronal mass ejections, CMEs, that occur. During solar maximum, the peak of the cycle, the sun produces more sunspots, dark, cooler regions on its surface where intense magnetic activity is concentrated. These sunspots often give rise to powerful solar flares, which are sudden bursts of radiation that can release energy equivalent to billions of atomic bombs in just minutes. Even more dramatic are CMEs, huge eruptions of charged particles that are blasted into space at speeds of millions of kilometers per hour. If these charged particles reach Earth, they can interact with our planet's magnetic field, creating breathtaking auroras in the polar regions. However, they can also cause significant disruptions, damaging satellites, interfering with GPS and radio communications, and even triggering widespread power outages. A particularly powerful solar storm, like the Carrington event of 1859, demonstrated the potential hazards of intense solar activity. During this event, a massive CME struck Earth, inducing electric currents that caused telegraph systems to fail and even set some telegraph offices on fire. If a similar storm were to occur today, it could have catastrophic consequences for our modern technological infrastructure, potentially crippling power grids, disrupting global internet connectivity, and damaging critical satellites that support communication and navigation systems. Scientists and space agencies around the world are working to develop early warning systems and protective measures to safeguard against the effects of extreme space weather. Despite its stability on human timescales, the sun is constantly evolving and its future holds dramatic changes. Right now, it is in the middle of its life, about 4.6 billion years old, and steadily burning through its vast reserves of hydrogen fuel. As nuclear fusion continues in its core, the sun gradually brightens, increasing its energy output over millions of years. This slow brightening has long-term consequences for Earth, as it leads to gradual warming, affecting our climate and the stability of our biosphere. However, the most significant transformations are still billions of years away. In around 5 billion years, the sun will exhaust its hydrogen fuel in the core and enter a new phase of its life cycle. At this stage, fusion will shift to helium, producing heavier elements such as carbon and oxygen. As a result, the Sun will expand into a red giant, swelling to hundreds of times its current size. During this phase, it will engulf Mercury and Venus, and possibly even Earth. If Earth is not completely swallowed, it will be scorched beyond recognition, with its oceans boiled away and its atmosphere stripped into space, leaving behind a barren, lifeless world. Following the red giant phase, the Sun will undergo a final transformation. It will shed its outer layers, creating a planetary nebula, a glowing shell of ionized gas that will drift through space, illuminating the surrounding regions. This nebula will eventually disperse, leaving behind the Sun's core, which will become a white dwarf. A white dwarf is an incredibly dense remnant, roughly the size of Earth but containing about half the Sun's mass. No longer undergoing fusion, it will gradually cool over billions of years, radiating away its remaining heat until it becomes a cold, dark black dwarf. A fate that awaits all low to medium mass stars. While the ultimate fate of the Sun is billions of years away, its shorter-term behavior still has a profound impact on our planet. From solar storms that can disrupt our technology to its gradual brightening that slowly warms Earth over millions of years, the Sun's influence is inescapable. Understanding the Sun is not just a matter of scientific curiosity. It is essential for protecting our technological civilization and preparing for the distant future. By studying solar activity, scientists can develop better space weather forecasting models, allowing us to mitigate the risks posed by solar storms and other potentially hazardous events. However, while the Sun's long-term changes are inevitable, our planet faces more immediate threats that require urgent attention. Climate change, driven by human activities such as fossil fuel combustion and deforestation, poses a serious challenge to life on Earth. Rising temperatures, melting ice caps, and extreme weather events are already reshaping ecosystems and threatening biodiversity. Additionally, asteroid impacts, though rare, remain a potential existential threat, with space agencies actively tracking near-Earth objects to assess potential collision risks. Humanity's survival in the coming centuries will depend on how well we address these challenges, ensuring that life continues to thrive even as our cosmic environment changes. The Sun, the very star that made life on Earth possible, will one day bring our planet's existence to an end. But before that distant future arrives, it will continue to shape our world in ways both subtle and profound. By deepening our understanding of the Sun, we not only prepare for its long-term changes, but also equip ourselves to navigate the challenges of our present and future. Through science, technology, and foresight, we can ensure that life endures, adapting to the ever-changing nature of our cosmic home. Earth's history is marked by cycles of creation and destruction, with life repeatedly flourishing and then being devastated by catastrophic events. Over the past 540 million years, the planet has experienced 5 major mass extinctions, each wiping out a significant portion of life and reshaping the evolutionary path of the survivors. These events were caused by a variety of natural disasters, from asteroid impacts to massive volcanic eruptions and even dramatic shifts in climate. Scientists now believe that Earth may be on the brink of a 6th mass extinction, this time driven by human activity. If history is any indication, life on Earth will eventually face another cataclysm. But the real question is whether humanity will survive it. The first of Earth's great mass extinctions, the Ordovician-Silurian extinction, occurred around 443 million years ago. At that time, most life was in the oceans, with no plants or animals yet living on the land. A sudden drop in global temperatures triggered massive glaciation, locking much of the planet's water in ice. This caused sea levels to plummet, destroying shallow marine habitats and killing off around 85% of all species. Over time, volcanic activity released greenhouse gases, warming the planet and ending the Ice Age. But by then, the damage was done. Around 374 million years ago, the late Devonian extinction struck, lasting for millions of years and gradually eliminating about 75% of species. While the exact cause remains debated, many scientists suspect that extensive volcanic activity led to environmental instability. Some theories also suggest that a comet or asteroid impact could have triggered the event, or that the evolution of the first land plants altered the climate by drawing down carbon dioxide from the atmosphere. Then came the most devastating mass extinction of all, the Permian-Triassic extinction, often called the Great Dying. Occurring around 252 million years ago, this event wiped out a staggering 96% of marine species and 70% of land species. Massive volcanic eruptions in what is now Siberia released enormous amounts of carbon dioxide, causing rapid global warming. This led to ocean acidification, oxygen depletion, and the destruction of entire ecosystems. The sheer scale of this disaster nearly ended complex life on Earth, but a few species survived, setting the stage for the age of dinosaurs. The next great extinction, the Triassic-Jurassic event, occurred around 201 million years ago. This period saw another wave of intense volcanic eruptions, which triggered a chain reaction of environmental changes, including global warming and ocean acidification. The extinction cleared the way for dinosaurs to dominate the planet, as many of their competitors were wiped out. Finally, the most famous mass extinction occurred 66 million years ago, the Cretaceous-Paleogene extinction, which brought an end to the age of dinosaurs. A massive asteroid, estimated to be about 10 kilometers wide, struck what is now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a nuclear winter effect as dust and debris blocked out the sun. Temperatures plummeted, plant life collapsed, and the food chain unraveled. Only small, adaptable creatures, including the ancestors of modern mammals, managed to survive. Today, scientists warn that Earth is in the early stages of a sixth mass extinction, driven not by natural disasters, but by human activity. Habitat destruction, pollution, climate change, and the rapid loss of biodiversity all mirror patterns seen before previous mass extinctions. Species are disappearing at rates thousands of times higher than the natural background extinction rate, leading some to call this the Anthropocene extinction. Climate change is a particularly serious threat. Since the Industrial Revolution, the burning of fossil fuels has released vast amounts of carbon dioxide into the atmosphere, trapping heat and altering global weather patterns. If temperatures continue to rise, extreme weather events will become more frequent. Sea levels will rise, and entire ecosystems could collapse. The last time Earth experienced such rapid climate change was during the Permian-Triassic extinction, and that ended in disaster. Another possible cause of a future mass extinction is an asteroid impact. NASA and other space agencies actively track near-Earth objects, searching for any that might pose a danger. The most concerning asteroid in the near future is Apophis, which will pass extremely close to Earth in 2029. While it is not expected to hit, its proximity serves as a reminder that Earth is still vulnerable to cosmic threats. A large enough impact could cause wildfires, tsunamis, and a collapse of the global food chain, just as it did for the dinosaurs. Supervolcanoes also pose a potential danger. The eruption of a supervolcano, such as Yellowstone in the United States, could eject thousands of cubic kilometers of ash into the atmosphere, blocking sunlight and triggering a volcanic winter. This could cause widespread famine, disrupt global supply chains, and potentially lead to the collapse of human civilization. Some researchers believe that a supervolcanic eruption contributed to the near extinction of early humans around 74,000 years ago, when the Toba eruption in Indonesia caused a severe drop in global temperatures. If another mass extinction occurs, the question remains, could humans survive? Unlike the dinosaurs, humans have intelligence, technology, and the ability to adapt to extreme conditions. However, a mass extinction would still be devastating, potentially leading to the collapse of modern civilization. Food and water shortages, economic collapse, and societal breakdowns could make survival extremely difficult. One possible way for humanity to safeguard itself is by becoming a multi-planetary species. If humans establish colonies on the Moon, Mars, or beyond, it would reduce the risk of being wiped out by a single catastrophic event. Space agencies and private companies, including NASA and SpaceX, are actively working toward this goal, developing technology to make space colonization a reality. While the future is uncertain, history has shown that life on Earth is resilient. Even in the face of mass extinctions, life has always found a way to recover and evolve into new forms. Whether humanity will be part of that future depends on how well we prepare for the challenges ahead. Even if Earth is ultimately doomed, could we find a new home among the stars? Scientists are searching for habitable planets beyond our solar system, hoping that one day we might discover a world capable of supporting human life. The dream of interstellar travel may still be far away, but if the survival of our species depends on it, humanity may one day take its place among the stars. For as long as humans have gazed up at the night sky, Mars has been a source of fascination and curiosity. It is the most Earth-like planet in our solar system, sharing some striking similarities with our home world. Mars has a 24.6-hour day, experiences seasonal changes due to its axial tilt, and possesses polar ice caps that expand and shrink with the seasons. Geological evidence suggests that Mars was once a much warmer and wetter world, covered in rivers, lakes, and possibly even oceans. Today, however, the planet is an arid, frozen wasteland, with an atmosphere so thin that liquid water cannot persist on its surface. Despite these harsh conditions, many scientists and visionaries believe that Mars could be humanity's next home. Colonizing the red planet would be the most ambitious and challenging endeavor in human history. But what would it actually take to turn this dream into a reality? Mars is the closest planet to Earth with any realistic potential for human habitation. Unlike Venus, which is a literal hellscape with surface temperatures hot enough to melt lead and an atmosphere dense with sulfuric acid clouds, Mars, at least in theory, is survivable with the right technology. The planet has vast reserves of water ice locked beneath its surface, a stable ground for construction, and enough sunlight to generate power through solar panels at 63 degrees Celsius. Near the poles, winter temperatures can plummet to minus 125 degrees Celsius, colder than the coldest places on Earth. Any human settlement would require advanced insulation and heating systems to maintain survivable conditions. Then there is the issue of the Martian atmosphere, or rather, the lack of a breathable one. Mars's atmosphere is about 100 times thinner than Earth's and is composed mostly of carbon dioxide, with only trace amounts of oxygen. Humans would be unable to breathe unassisted, meaning colonists would have to bring their own oxygen supply or find ways to generate it on Mars. One promising technology is NASA's MOXIE experiment, which has successfully demonstrated the ability to extract oxygen from Martian air by splitting carbon dioxide molecules. However, scaling up this process to support an entire colony would be a significant engineering challenge. Mars's lower gravity is another factor that could affect long-term colonization. The planet has only 38% of Earth's gravity, meaning that everything, including human bodies, would weigh less. While this might seem advantageous at first, prolonged exposure to low gravity could have detrimental effects on human health. Astronauts on the International Space Station, who experience near weightlessness, suffer from muscle loss, bone density reduction, and fluid shifts in their bodies. Without proper countermeasures, Martian settlers might face similar problems, potentially leading to long-term health complications. Mars is also notorious for its massive dust storms. These storms, which can last for weeks or even months, sometimes grow large enough to cover the entire planet. The fine dust is not only a hazard for human lungs, but also a threat to equipment and solar panels, which would be a primary source of energy. Unlike storms on Earth, Martian dust storms are not driven by strong winds, but by the planet's thin atmosphere, which allows dust particles to remain suspended for extended periods. Some scientists have proposed an even grander idea: terraforming Mars, transforming it into a more Earth-like world by thickening its atmosphere and raising its temperature. The concept involves releasing greenhouse gases, such as carbon dioxide, to trap more heat and create a stable, warm climate. This could, in theory, melt the planet's ice caps, releasing more water and setting off a chain reaction that could make Mars habitable. Some more extreme proposals even suggest detonating nuclear explosions at the poles to release trapped gases quickly. However, recent studies indicate that Mars may not have enough carbon dioxide in its surface and atmosphere to sustain a terraforming effort. Even if it were possible, the process would likely take thousands or even millions of years to complete. Instead of changing the entire planet, a more realistic approach may involve building enclosed, self-sustaining habitats, domed cities or underground bases where conditions could be carefully controlled. Before humans can set foot on Mars, we must first return to the Moon. NASA's Artemis program is designed to establish a permanent lunar base, serving as a testing ground for the technologies and survival strategies needed for long-duration missions on Mars. The experience gained from living and working on the Moon, developing resource extraction techniques, testing radiation shielding, and learning to operate in an isolated environment will be invaluable for future Mars missions. If Artemis is successful, NASA aims to send the first astronauts to Mars in the late 2030s or early 2040s. Meanwhile, SpaceX is taking an even more ambitious approach. Elon Musk, the CEO of SpaceX, has made it clear that his ultimate goal is to make humanity a multi-planetary species. His company is developing Starship, a fully reusable spacecraft capable of carrying up to 100 people at a time. Musk envisions fleets of Starships launching every 26 months, the period when Mars and Earth are at their closest, to transport settlers, equipment, and supplies to the Red Planet. His long-term goal is to build a self-sustaining city on Mars, with industries, agriculture, and eventually an independent Martian economy. Of course, such a vision faces immense challenges. Transporting enough materials and people to Mars would require thousands of launches and an enormous financial investment. Additionally, any Mars settlement would remain heavily dependent on Earth for food, medicine, and spare parts for a long time, making it vulnerable to disruptions. Psychological factors also come into play. How will humans cope with the isolation? The knowledge that they are tens of millions of kilometers away from the nearest help, and the sheer alien nature of their new world. Despite these hurdles, humanity's future may very well depend on expanding beyond Earth. Our planet is vulnerable to numerous threats: climate change, asteroid impacts, supervolcanic eruptions, and even the distant but inevitable evolution of the Sun. Colonizing Mars would be a form of insurance for our species, ensuring that even if catastrophe strikes Earth, human civilization can continue elsewhere. While a thriving Martian colony may still be decades or even centuries away, we are steadily making progress. Robotic missions like NASA's Perseverance rover are currently exploring Mars, testing new technologies and searching for signs of ancient life. The development of Starship and other next-generation spacecraft brings us closer to the day when the first humans will walk on the Red Planet. The pioneers who take that first step will face challenges unlike any seen before. They will endure extreme cold, radiation, and isolation, but if they succeed, they will take the first step toward making humanity a spacefaring civilization, one no longer confined to a single planet, but capable of reaching for the stars. But what if we could go even further than Mars? For all of humanity's achievements in space exploration, we are still confined to our own cosmic backyard. Even reaching Mars, the closest planet that could potentially support life, remains a monumental challenge. But what about venturing beyond our solar system? Could we ever travel to another star and set foot on an alien world? The idea of interstellar travel has captured the imagination of scientists and science fiction writers alike. But the reality is far more daunting than we often realize. The biggest obstacle to interstellar travel is distance. Our closest neighboring star system, Alpha Centauri, is over 4 light-years away. To put that into perspective, 1 light-year is nearly 10 trillion kilometers. Even with the fastest spacecraft ever built, it would take tens of thousands of years to reach Alpha Centauri. And that is just the closest star. Most of the promising exoplanets where life might exist are dozens, hundreds, or even thousands of light years away. The fundamental problem is speed. The fastest spacecraft humans have ever launched, the Parker Solar Probe, travels at around 700,000 kilometers per hour. That sounds incredibly fast, but even at that speed, it would take over 6,000 years to reach Alpha Centauri. The laws of physics, as we understand them, impose strict limits on how fast we can travel. The ultimate speed limit is the speed of light, about 300 million meters per second. According to Einstein's theory of relativity, as an object approaches the speed of light, its mass increases, and it requires more and more energy to accelerate. In practical terms, this means that reaching even a fraction of light speed requires enormous amounts of energy, far beyond what our current technology can provide. Despite these challenges, scientists have proposed several theoretical solutions for interstellar travel. One of the most famous concepts is the idea of a warp drive, a technology that could bend space-time itself to allow faster-than-light travel. The idea comes from Einstein's equations, which suggest that space-time can be warped by massive objects like black holes. If we could somehow create a bubble of distorted space-time around a spacecraft, it might be possible to compress space in front of the ship and expand it behind, allowing the spacecraft to move faster than light without technically violating the laws of physics. One of the most well-known warp drive concepts is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. According to his theory, a spacecraft could create a space-time bubble that moves faster than light. However, this would require an exotic form of matter with negative energy, something that has never been observed and may not even be possible to create. While the concept is fascinating, it remains purely theoretical, with no known way to build such a device. Since faster-than-light travel remains out of reach, another possibility is sending spacecraft that travel at a significant fraction of light speed. One proposed method is using light sails, giant, ultra-thin sails propelled by powerful lasers. The Breakthrough Starshot initiative, for example, aims to develop tiny spacecraft that could be accelerated to 20% of the speed of light using laser propulsion. If successful, such a spacecraft could reach Alpha Centauri in about 20 years. However, even this approach presents huge technical challenges, including the need for an enormous laser array on Earth and the difficulty of slowing down upon arrival. If we cannot send humans at high speeds, we might have to take a much slower approach, using generation ships. A generation ship would be a massive spacecraft designed to sustain multiple generations of humans as they travel to another star system. The journey might take hundreds or thousands of years, meaning that the people who arrive at the destination would be the distant descendants of the original crew. Generation ships would need to function as self-sufficient ecosystems, capable of producing food, recycling air and water, and maintaining life support systems for centuries. This presents enormous engineering and social challenges. How do you ensure that a society remains stable and functional over many generations? How do you prevent technological decay or psychological strain from isolation? Some experts believe that long-duration space travel could lead to major societal issues, including rebellion, loss of knowledge, or even the failure of the mission before arrival. Another alternative is cryosleep, or suspended animation. If humans could be placed in a state of deep hibernation, they could survive long journeys without needing to consume food or interact with their environment. While this concept is common in science fiction, real-world cryonics is still in its early stages. Current cryopreservation techniques can freeze biological tissue, but reviving a living human from a frozen state is far beyond our capabilities. Even if we could develop a working cryosleep system, there would still be challenges in ensuring the safety and well-being of travelers over such long timescales. An entirely different approach could be sending artificial intelligence instead of humans. Instead of launching fragile biological beings across the vastness of space, we could send robotic probes equipped with advanced AI. These probes could explore distant star systems, send back data, and even build infrastructure in preparation for future human arrivals. Some scientists have even speculated about the possibility of uploading human consciousness into machines. allowing digital humans to travel across the stars without the limitations of a physical body. Even if we develop a way to reach other star systems, there is another problem: finding a suitable destination. While thousands of exoplanets have been discovered, most are completely inhospitable. Many are gas giants, super-Earths with crushing gravity, or planets locked in tidal heating cycles that make them extreme wastelands. The few potentially habitable exoplanets that exist are still light years away, meaning that any interstellar mission would need to be incredibly well planned. Our current knowledge of exoplanets comes mostly from indirect observations, measuring the dimming of a star as a planet passes in front of it, or detecting the gravitational wobble caused by a planet's orbit. These methods give us estimates of size, mass, and atmospheric composition, but they cannot provide details about surface conditions or the presence of life. Future telescopes, such as the James Webb Space Telescope and other next-generation observatories, may help us identify truly Earth-like exoplanets. But even if we find a suitable world, reaching it remains a seemingly insurmountable challenge. If humans do manage to travel to another star system, what will they find? Will they discover a planet with vast oceans and breathable air, or will they encounter an inhospitable rock covered in toxic gases? And if an Earth-like world is found, would it already harbor life? If so, ethical and biological concerns arise. How would our presence affect any native ecosystems? Would we be invaders, disrupting a delicate balance, or would we find a place to coexist? The answers to these questions remain unknown, adding yet another layer of complexity to the dream of interstellar travel. Given all these obstacles, will humanity ever become an interstellar civilization? Some scientists are optimistic, believing that future breakthroughs in physics could make faster-than-light travel possible. Others argue that even if interstellar travel is extremely difficult, it is not impossible. Humans have a history of overcoming seemingly insurmountable challenges. Just as our ancestors crossed vast oceans to explore new lands, perhaps one day we will venture across the stars. For now, interstellar travel remains a dream. Our best hope lies in continued research, technological advancements, and the steady expansion of human presence into space. While reaching another star may take centuries or even millennia, every step we take, from exploring Mars to building better propulsion systems, brings us closer to that distant goal. One of the greatest challenges of interstellar travel is not just reaching another star, but ensuring the survival of those making the journey. Space is a harsh environment filled with dangers, from deadly radiation to the psychological toll of prolonged isolation. Any long-duration mission beyond our solar system would need to account for these hazards. Unlike short missions to the Moon or even Mars, where emergency evacuations could be theoretically possible, interstellar journeys would leave astronauts completely cut off from Earth, making self-sufficiency a critical requirement. Radiation exposure is one of the most significant threats. Beyond the protective shield of Earth's atmosphere and magnetosphere, space is flooded with cosmic rays, high-energy particles that can damage DNA, increase the risk of cancer, and harm electronic systems. A journey lasting decades or centuries would expose travelers to far higher doses of radiation than anything experienced on the International Space Station. Shielding against this radiation is difficult because traditional materials like lead or aluminum would make the spacecraft too heavy. Scientists have explored alternative solutions, such as using water, hydrogen-rich plastics, or even magnetic shields to deflect radiation, but none are perfect solutions yet. Another serious problem is the effect of long-term space travel on the human body. Even after just a few months in microgravity, astronauts experience muscle atrophy, bone density loss, and vision problems. On a multi-generational journey, these issues would be magnified. Without the constant pull of gravity, humans could experience irreversible physical changes, potentially making it impossible for them to adapt to life on a new planet if they ever arrived. Some scientists suggest that spacecraft could be designed to rotate, creating artificial gravity through centrifugal force. However, building and maintaining such a system over interstellar distances would be an enormous engineering challenge. Beyond the physical effects, there are also deep psychological and sociological concerns. A small group of humans living in isolation for generations could experience intense stress, depression, and potential conflicts. Social dynamics could evolve in unpredictable ways, and without a stable societal structure, a mission could easily collapse. History has shown that even isolated communities on Earth, despite access to supplies and communication, have struggled with internal divisions. A mission lasting hundreds of years would need a well-planned governance system, strict population control measures, and cultural stability to ensure survival. One possible way to mitigate these issues is by automating as much of the journey as possible. Advanced AI and robotics could help maintain spacecraft systems, manage resources, and even assist with decision-making. A highly autonomous ship could function more like a self-sustaining ecosystem, reducing the burden on human passengers. Some researchers have even proposed that an interstellar mission could be carried out entirely by AI-driven probes, which could prepare a distant world for eventual human colonization. If we cannot send living humans across the stars, perhaps our first step will be robotic emissaries, paving the way for future settlers. Even if we develop the technology to reach another star, another issue remains: finding a suitable planet to colonize. Many of the exoplanets discovered so far are hostile environments with extreme temperatures, crushing gravity, or toxic atmospheres. While a handful of Earth-like candidates exist, their true habitability remains unknown. Future missions will need to analyze these distant worlds in far greater detail before committing to an interstellar journey. The challenge of identifying a second Earth is not just about finding the right size and location. It also requires understanding atmospheric composition, magnetic field strength, and whether the planet has liquid water. Terraforming is another potential solution. If we find a planet that is close to being habitable but not quite ideal, we might be able to alter its environment to make it more suitable for human life. This concept has been explored for Mars, where proposals include releasing greenhouse gases to warm the planet, melting polar ice caps, and even engineering microbes to produce oxygen. However, the scale of such a project on an exoplanet would be staggering. It could take thousands of years to turn an alien world into a true second home for humanity. Despite all these challenges, some scientists believe interstellar travel is not just possible, but inevitable. They argue that human civilization must eventually expand beyond Earth to ensure long-term survival. Our planet is vulnerable to natural disasters, climate change, and even cosmic threats like asteroid impacts or supernova explosions. The only way to guarantee the future of our species is to spread out across the stars, reducing the risk of extinction. However, there is also the possibility that interstellar expansion might not be the answer. Some argue that instead of physically traveling to other stars, we should focus on advancing our knowledge and technology right here at home. Perhaps breakthroughs in artificial intelligence, virtual reality, or quantum computing will change the way we think about space exploration. Maybe we will find a way to explore distant planets through remote probes, or even upload human consciousness into digital form, removing the need for physical travel altogether. In the end, the dream of interstellar travel reflects something deeply ingrained in human nature: our relentless curiosity and desire to explore. Even if the challenges seem insurmountable, history has shown that what once seemed impossible can eventually become reality. While we may not be ready to journey to the stars just yet, each new discovery in physics, propulsion, and space exploration brings us one step closer. Even if we could reach other stars, we might still be trapped in our cosmic neighborhood. The universe, in all its vastness, stretches far beyond the limits of our understanding. What we observe is only a fraction of what exists, a mere glimpse into the cosmic expanse that extends well beyond our reach. The observable universe, which measures about 93 billion light-years across, represents only the portion of the cosmos from which light has had time to travel to us since the Big Bang. This boundary is not a physical edge, but a limit imposed by the speed of light and the passage of time. The further we look, the further we peer into the past. Yet, the light from the farthest reaches of space will never be able to reach us, because the universe is expanding at an ever-accelerating rate. The size of the universe is a concept that defies comprehension. While we can measure the observable universe, the true scale of the cosmos may be far beyond our imagination. If the universe is indeed infinite, then what we see is just a tiny patch in an ever-expanding sea of stars and galaxies. But if the universe is finite, then what exists beyond the observable limit is an even more profound mystery. Is it simply empty space, or is there something more? And if the universe has an edge, what exists beyond that? The questions we are left with about the true size and nature of the universe are vast and endless. To grasp this idea more clearly, consider the concept of the cosmic horizon. The cosmic horizon is a boundary defined by the speed of light and the rate of expansion. The universe's expansion means that parts of the cosmos are moving away from us faster than the speed of light. This is not a violation of the laws of physics, but an inevitable consequence of the fabric of space itself stretching. Some regions of the universe, due to their speed and the nature of cosmic expansion, are already beyond our reach. No matter how advanced our technology becomes, we will never be able to observe or interact with these far-off regions, because their light can no longer reach us. As we look further into space, we not only peer deeper into the cosmos, but also further back in time. The further we look, the older the light is, and the more we see the universe as it existed billions of years ago. The light from galaxies near the cosmic horizon is ancient, traveling billions of years to reach us. However, many of these galaxies have long since moved beyond our view, leaving us with only a snapshot of their distant past. This phenomenon, while fascinating, also underscores the transient nature of the universe. As the universe expands, more regions will fade from view, lost to time and space forever. This cosmic horizon represents a significant limitation. It is not just an observational boundary, but a barrier to understanding the true nature of the universe. If the universe extends far beyond the observable region, what lies beyond? Some scientists speculate that space might continue uniformly, with galaxies stretching endlessly into the void. Others propose that the universe beyond our view could have different physical laws governing it, potentially creating entirely different realities. This raises the tantalizing possibility of a multiverse, an infinite collection of universes, each with its own set of rules and constants. The concept of the multiverse suggests that our universe might be just one of many, a bubble in a sea of cosmic bubbles. These other universes, if they exist, could be fundamentally different from ours. The laws of physics, the constants of nature, and the very fabric of space-time could vary from one universe to the next. Perhaps in another universe, the fundamental forces operate differently, or the laws of gravity are not as we know them. If the multiverse hypothesis is correct, our universe could be a small and relatively unremarkable part of an infinite and unimaginably diverse cosmos. Yet, even within the observable universe, there are significant limitations. One of the most profound barriers to our understanding is the cosmic microwave background, CMB, the afterglow of the Big Bang. This faint radiation marks the oldest light we can detect, originating from the time when the universe was only about 380,000 years old. Before this time, the universe was opaque, filled with a hot, dense plasma that prevented light from traveling freely. As the universe cooled, atoms formed, and light could finally travel through space. This moment, known as the decoupling of light, marks the beginning of the era that we can observe. However, this wall of light, while offering valuable insights into the early universe, also marks the limit of our vision. No matter how advanced our technology becomes, we will never be able to see beyond this point, leaving the first moments of the universe permanently hidden from direct observation. While we cannot observe what happened before the CMB, scientists have developed theories about the early universe using mathematical models and the laws of physics. These models allow us to make educated guesses about the conditions that existed before the universe cooled enough for light to travel freely. However, these theories are speculative, and without direct evidence, we cannot know for certain what the universe was like in its infancy. The inability to peer into the very beginning of the universe is a humbling reminder of the limitations of our knowledge. As if these cosmic horizons and barriers to observation were not enough, the mysteries of the universe grow even more complex when we consider the microscopic realm. While the vastness of space challenges our understanding of scale, the strange and unpredictable behavior of particles at the quantum level defies all logic. Quantum mechanics, the theory that governs the smallest scales of the universe, is a world unlike any other. In the quantum realm, particles exist in multiple states at once. Probabilities govern their behavior, and uncertainty is inherent to the system. At the quantum level, the rules of classical physics, those that govern the motions of planets, stars, and galaxies, break down. The predictable, deterministic world we experience on a macroscopic scale gives way to a realm of uncertainty, where particles can be in multiple places at once, and their behavior can only be described probabilistically. This strange and counterintuitive world of quantum mechanics challenges our most fundamental assumptions about the nature of reality. It forces us to confront the possibility that our entire understanding of the universe, built on centuries of observation and experimentation, may be incomplete. In the quantum world, space and time themselves become fluid. The very fabric of space-time can be warped and twisted, and particles can interact in ways that seem to defy the rules of causality. These phenomena, while fascinating, are still not fully understood, and their implications for our understanding of the cosmos are profound. Could the mysteries of quantum mechanics hold the key to unlocking new dimensions of reality? What secrets might lie hidden within the quantum world, waiting to be discovered? Just as the vastness of the universe challenges our understanding of space, the mysteries of quantum physics challenge our understanding of time, causality, and reality itself. In many ways, quantum mechanics may be the next frontier of human exploration, a realm where the rules of the universe are rewritten, and where our deepest questions about the nature of existence may find answers. But beyond space, the mysteries of quantum physics challenge our understanding even further. The implications of quantum mechanics extend far beyond the realm of particle physics. In fact, quantum phenomena have the potential to change everything we know about the universe. One of the most mind-boggling aspects of quantum theory is the concept of superposition. This principle suggests that particles can exist in multiple states at once, each with its own probability. For example, an electron might be both here and there at the same time, a reality that defies all classical understanding. It's only when we measure or observe these particles that they collapse into one definite state, a process that quantum physicists still struggle to fully explain. This behavior challenges our most basic intuitions about how the world works. It seems as though the universe at the quantum level is not deterministic in the way that larger scales are. If we think of the macroscopic world as a well-oiled machine, governed by predictable laws, the microscopic world is chaotic and probabilistic, where certainty is not guaranteed. This leaves us with a sense that, at its core, reality is uncertain. The more we learn about quantum mechanics, the more we realize that what we know about the universe may just be the surface of a much deeper, far stranger reality. The mysteries don't end there. Another perplexing phenomenon in quantum mechanics is quantum entanglement, a phenomenon where two particles become entangled in such a way that the state of one particle is instantly connected to the state of another, regardless of the distance between them. This means that even if the particles are light years apart, a change in one will instantaneously affect the other. Albert Einstein famously referred to this as spooky action at a distance, and although experiments have proven that entanglement is real, its implications remain unclear. Some physicists speculate that entanglement could be a key to understanding the fabric of space-time, perhaps offering insights into how distant parts of the universe are connected, or even suggesting that space itself is not the continuous entity we once thought it was. Quantum physics suggests that the universe might be far more interconnected and bizarre than we can fathom. The very concept of locality, the idea that objects are only influenced by their immediate surroundings, breaks down at quantum scales. Instead, particles seem to be connected in ways that transcend our traditional understanding of space and time. This raises a staggering possibility. What if the fundamental nature of reality itself is radically different from what we experience? Could our perception of the universe as a collection of isolated objects be an illusion, masking a much deeper, interconnected fabric of reality? In addition to these puzzles, quantum mechanics also opens up the possibility of parallel universes or alternate realities. Some versions of quantum theory, such as the many worlds interpretation, suggest that every time a quantum event occurs, the universe splits into multiple versions, each reflecting a different outcome. This implies that an infinite number of parallel universes might exist, each with its own version of events, where every possible outcome of a quantum event has played out in some universe. This interpretation challenges our very conception of reality and suggests that the multiverse might be far more complicated and expansive than we ever imagined. While these concepts remain speculative, they are not entirely beyond the realm of scientific inquiry. Over the past few decades, scientists have devised ways to test quantum theory, and the results have consistently matched predictions. Experiments like those involving the double-slit experiment and quantum teleportation have confirmed that the quantum world is indeed strange and unpredictable. Yet, despite this progress, many questions remain unanswered, and there are still deep mysteries surrounding the fundamental nature of reality itself. As quantum mechanics progresses, new technologies based on these principles are already beginning to emerge. Quantum computing, which harnesses the power of quantum states to perform complex calculations at unimaginable speeds, promises to revolutionize fields ranging from artificial intelligence to cryptography. Quantum encryption, based on the principles of quantum mechanics, could create unbreakable communication systems that are immune to hackers. These advances are just the tip of the iceberg, and as we develop the ability to manipulate the quantum world, our understanding of the universe could change drastically. The very nature of information, computation, and reality itself could be rewritten in the quantum age. This leads us to consider a radical thought. Could the universe itself be a quantum system, its fundamental particles entangled in a cosmic dance, with the laws of physics emerging from deeper, hidden layers of reality? As we uncover the secrets of quantum mechanics, we might find that the entire universe is governed by principles that we have yet to fully understand. These principles could be the keys to unlocking the deepest mysteries of existence, offering answers to questions that have haunted humanity for millennia. Yet, even as we peer into the subatomic world, we are still bound by the limitations of our tools and our understanding. The quantum realm remains shrouded in uncertainty and complexity, and it is clear that we are only scratching the surface of its secrets. As our knowledge of quantum physics expands, we might discover new phenomena that challenge our very notions of space, time, and reality. Perhaps we will one day develop the technology to manipulate quantum states at will, opening doors to possibilities that we can only dream of today. This brings us to the final frontier of scientific exploration, the search for a unified theory of everything. For centuries, physicists have searched for a single framework that can explain all the forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Currently, the two most successful theories in physics, general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which explains the behavior of particles at the smallest scales, remain incompatible. The quest for a unified theory, often referred to as the theory of everything, has driven much of modern physics. This theory would be the holy grail of science, providing a single equation that could explain the workings of the universe from the smallest quantum particles to the largest galaxies. The search for a unified theory is not just about solving a scientific puzzle, it's about deepening our understanding of the cosmos and our place within it. By unlocking the secrets of both the large and small scales of the universe, we may be able to grasp the very essence of reality itself. Whether or not such a theory is achievable remains to be seen, but the quest continues, pushing the boundaries of human knowledge. As we continue to explore both the vastness of space and the mysteries of the quantum world, one thing is clear: the universe is far more complex and mysterious than we can ever truly comprehend. We may never be able to fully understand the nature of reality, but with each discovery, we get closer to answering the most profound questions about the cosmos and our place within it. The universe is an enigma, but through science, observation, and exploration, we inch ever closer to unlocking its secrets. And perhaps, in doing so, we will not only better understand the cosmos, but also the very nature of existence itself. But beyond space, the mysteries of quantum physics challenge our understanding even further. At the smallest scales of existence, the universe behaves in ways that defy logic and intuition. Unlike the predictable motion of planets, stars, and galaxies governed by classical physics, the quantum realm is ruled by uncertainty, probability, and interactions that seem to defy the very fabric of reality. Quantum mechanics is the branch of physics that describes this microscopic world, where particles can exist in multiple states at once, influence each other instantly across vast distances, and even behave as both particles and waves. This bizarre and counterintuitive nature of reality suggests that the universe is far more complex than we ever imagined. While Newtonian physics explains how objects move and interact on large scales, quantum mechanics reveals that, at its core, reality is not as solid or deterministic as we once believed. One of the strangest and most baffling aspects of quantum mechanics is the phenomenon of quantum entanglement, where two particles become linked in such a way that changes to one instantly affect the other, no matter how far apart they are. This connection happens faster than the speed of light, violating our normal understanding of space and time. If one entangled particle is measured and found to be in a particular state, its partner will instantly assume a corresponding state, even if they are light years apart. Albert Einstein famously referred to this as spooky action at a distance, because it seemed to contradict his theory of relativity, which states that no information can travel faster than light. Despite how bizarre this seems, quantum entanglement has been experimentally confirmed multiple times, and scientists are now exploring whether it could be used for faster-than-light communication, quantum teleportation, or even the development of ultra-secure quantum computers. Another fundamental mystery of quantum mechanics is the double-slit experiment, which demonstrates that particles such as electrons and photons can behave as both waves and particles, depending on how they are observed. In this experiment, when a beam of particles is directed at a barrier with two narrow slits, the pattern that appears on a screen behind the barrier is not what one would expect if the particles traveled through only one slit or the other. Instead, they form an interference pattern, as if each particle traveled through both slits simultaneously like a wave. However, the moment a measurement is made to determine which slit a particle passes through, the wave-like interference disappears, and the particle behaves as if it only went through one slit. This suggests that the mere act of observation influences the outcome, raising profound questions about the nature of reality and the role of consciousness in shaping the physical world. It implies that at the fundamental level, the universe does not have a definite state until it is observed, leading to deep philosophical debates about the nature of existence itself. These strange behaviors of quantum mechanics have led to speculation that they may be linked to some of the biggest mysteries in cosmology, such as black holes and dark matter. Black holes are thought to warp space and time to such an extreme degree that quantum effects become crucial in describing what happens inside them. Some theories propose that black holes store information in a way that is deeply connected to quantum entanglement, suggesting that space and time themselves may emerge from quantum processes at the smallest scales. This idea is central to the holographic principle, which proposes that the three-dimensional universe we experience may actually be a projection of quantum information encoded on a two-dimensional surface at the edge of space. Another major mystery that quantum mechanics may help explain is the nature of dark matter, the invisible substance that makes up most of the universe's mass. Unlike ordinary matter, dark matter does not interact with light or electromagnetic forces, making it impossible to detect directly. Some scientists suggest that dark matter could be composed of unknown quantum particles that behave in ways we have yet to understand. There are even theories that link dark matter to hidden dimensions of space-time, suggesting that our universe might be just a small part of a much larger reality. If dark matter turns out to be a quantum phenomenon, it could provide crucial insights into the true nature of the cosmos. Quantum mechanics also challenges our understanding of time and causality. One interpretation of quantum physics, known as the many worlds interpretation, suggests that every quantum event results in the universe splitting into multiple parallel realities, each representing a different possible outcome. This means that every decision we make, every particle interaction, and every possible future exists simultaneously in an infinite number of alternate realities. While this idea remains highly speculative, it offers a potential explanation for the strange behavior of quantum systems and could have profound implications for our understanding of free will, consciousness, and the nature of time itself. One of the biggest challenges in modern physics is unifying quantum mechanics with general relativity, Einstein's theory that describes gravity and the large-scale structure of the universe. While quantum mechanics works exceptionally well at the microscopic level and general relativity accurately describes massive objects like planets and galaxies, the two theories are fundamentally incompatible. When scientists try to apply quantum mechanics to extremely strong gravitational fields, such as those inside black holes or at the moment of the Big Bang, the equations break down, suggesting that a deeper theory is needed. Many physicists believe that a theory of quantum gravity, possibly involving string theory or loop quantum gravity, will eventually provide a unified description of all physical forces. Despite all the progress made in quantum mechanics over the past century, many mysteries remain unsolved. Scientists still do not fully understand why quantum systems behave the way they do, or whether there is a deeper underlying reality that determines quantum outcomes. If a true theory of everything can be developed, it could revolutionize our understanding of the universe and provide answers to some of the deepest questions in physics. Until then, the quantum world remains a realm of paradoxes, probabilities, and unanswered questions, reminding us that the universe is far stranger than we ever imagined. As our understanding of quantum mechanics continues to evolve, it may unlock entirely new ways of thinking about space, time, and reality itself. The universe is vast and full of mysteries that continue to baffle scientists. While we have made incredible progress in understanding space, there are still many unexplained phenomena that challenge our current understanding of physics. Some of these mysteries could be the result of new physics waiting to be discovered, while others might reveal something even stranger about the nature of the cosmos. From strange stars to massive cosmic forces, these unsolved questions push the limits of our knowledge and imagination. One of the most intriguing mysteries is the unusual behavior of Tabby's star, officially known as KIC 8462852. This star, located about 1,400 light-years away, has shown strange and unpredictable dips in brightness that do not match the patterns of known astronomical objects like planets or dust clouds. While most stars experience small, regular dimming when planets pass in front of them, Tabby's star exhibits irregular and extreme drops in brightness, sometimes by as much as 22%. Scientists have proposed several possible explanations, including a swarm of comets, an unusually dense ring system, or even a massive dust cloud, but none of these fully explain the observations. This has led some researchers to speculate about a more exotic possibility, the presence of an alien megastructure, such as a Dyson sphere, a hypothetical massive structure built by an advanced civilization to harness a star's energy. While there is no evidence confirming this idea, the unusual nature of Tabby's star remains one of the most puzzling astronomical discoveries in recent years. Another cosmic enigma is the Great Attractor, a mysterious gravitational anomaly that appears to be pulling entire galaxies, including our own Milky Way, toward it. Located about 200 million light-years away, the Great Attractor lies in a region of space known as the Zone of Avoidance, an area obscured by the dense stars and dust of the Milky Way. This makes it difficult to observe directly, but its gravitational influence is undeniable. The Milky Way, along with thousands of other galaxies in our local supercluster, is moving toward this unseen force at a speed of over 2,200,000 km/h. What makes the Great Attractor so mysterious is that it does not seem to correspond to any massive visible structure, like a supercluster of galaxies, that could explain its immense gravitational pull. Some scientists believe it could be part of an even larger structure, such as the Shapley supercluster or the vast Laniakea supercluster, but its exact nature remains unknown. Understanding the Great Attractor could provide important clues about the large-scale structure of the universe and the unseen forces shaping its evolution. One of the deepest mysteries in physics is the apparent imbalance between matter and antimatter in the universe. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter, mirror image particles that annihilate each other upon contact. However, if this were the case, all matter should have been destroyed early in the universe's history, leaving behind only energy. Instead, we observe a universe filled with galaxies, stars, and planets made entirely of normal matter, with very little antimatter in sight. This asymmetry is one of the biggest unresolved problems in cosmology, and scientists are searching for explanations. Some theories suggest that unknown interactions during the early moments of the universe created a tiny imbalance, allowing matter to dominate over antimatter. Others propose that antimatter may exist in hidden regions of the universe, possibly forming entire antimatter galaxies. Solving this mystery is crucial, as it could reveal new physics beyond the standard model and help us understand the fundamental nature of the cosmos. Adding to the list of cosmic anomalies is a strange feature in the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB provides a snapshot of the early universe, and it is expected to be nearly uniform in all directions. However, scientists have discovered an unusual pattern in the CMB known as the axis of evil, a large-scale asymmetry that seems to challenge the idea that the universe is isotropic, or the same in all directions. This pattern suggests that some unknown physical process influenced the early universe in a way that current models cannot explain. Some researchers have proposed that this anomaly could be due to the shape of the universe itself, while others suggest it might be a statistical fluke. However, there is also the possibility that it hints at new physics, or even a connection to a larger, unseen structure beyond our observable universe. If the axis of evil is real and not just a coincidence, it could force scientists to rethink our understanding of the cosmos and its fundamental laws. These unexplained mysteries remind us that despite our advancements in astronomy and physics, there is still much we do not understand about the universe. Each of these enigmas represents a challenge to our current scientific theories and a potential doorway to new discoveries. If we can survive long enough as a species and continue advancing our technology, we may one day uncover the answers to these cosmic puzzles. And if humanity is truly destined to become a spacefaring civilization, we may eventually reach a level where we are not just studying the mysteries of the universe, we are shaping them. The fate of humanity is often imagined in terms of survival, exploration, and progress, but there is a grander perspective, one that considers our potential place in the cosmos as an advanced civilization. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a way to classify civilizations based on their ability to harness energy. This system, known as the Kardashev scale, describes three main types of civilizations, each more advanced than the last. Where does humanity currently stand on this scale? And could we ever ascend to the highest level, a Type 3 civilization that controls the power of an entire galaxy? Right now, humanity is not even a Type 1 civilization. We are currently classified as roughly 0.7 on the Kardashev scale, meaning we do not yet have the ability to harness all of the available energy on Earth. A true Type 1 civilization, also called a planetary civilization, would be capable of capturing and using the full energy potential of its home planet. This would include harnessing all solar, wind, geothermal, and nuclear power, as well as fully utilizing the planet's resources in a sustainable and efficient way. Some scientists estimate that humanity could reach Type 1 status within the next few hundred years, assuming we do not destroy ourselves first through war, climate change, or other self-inflicted disasters. Beyond that lies Type 2, the stage of a stellar civilization. A civilization at this level would be able to harness the full energy output of its star, potentially through a concept known as a Dyson sphere. A Dyson sphere, first proposed by physicist Freeman Dyson, is a theoretical megastructure that would completely surround a star and capture most or all of its energy. With this level of power, a Type 2 civilization could reshape entire planets, terraform worlds, and sustain an interplanetary empire. To achieve this, humanity would need to develop technology far beyond our current capabilities, including advanced fusion reactors, large-scale space industry, and artificial intelligence systems capable of managing such immense projects. This stage could take thousands of years to reach, assuming we continue to advance without catastrophic setbacks. The ultimate goal of the Kardashev scale is a Type 3 civilization, one that has mastered the energy of an entire galaxy. Such a civilization would be able to manipulate not just planetary and stellar systems, but entire clusters of stars, possibly even altering the structure of the Milky Way itself. A Type 3 society would require a vast, coordinated network of intelligent systems, possibly controlled by artificial intelligence far beyond anything we can imagine today. They could use black holes as energy sources, build structures on an interstellar scale, and perhaps even manipulate the fundamental fabric of space-time. If humanity ever reached this stage, we would no longer be limited to a single planetary or even stellar home. We would be a true galactic species, with our influence stretching across thousands or millions of light years. However, reaching this level presents enormous challenges. The greatest of these is survival. Many scientists believe that most intelligent civilizations never make it past a certain point. This idea is known as the Great Filter. It suggests that somewhere along the path, from a primitive species to an advanced spacefaring civilization, there is a barrier that very few, if any, civilizations manage to cross. This could be anything from self-destruction through nuclear war or climate change, to natural cosmic disasters like asteroid impacts, supernovae, or gamma-ray bursts. It might also be that civilizations inevitably stagnate or become dependent on artificial intelligence that eventually surpasses them. If the Great Filter exists ahead of us, then humanity might never become a Type 3 civilization at all. But what if we do survive? If we find a way to overcome war, environmental collapse, and resource depletion, we may one day step onto the path of interstellar expansion. By colonizing Mars, building space habitats, and eventually sending spacecraft beyond our solar system, we could begin the journey toward a more advanced status. Breakthroughs in energy production, artificial intelligence, and space travel could allow us to move from a planetary society to a truly spacefaring one. If we manage to reach Type 1, then Type 2, and eventually Type 3, we might become the dominant force in the galaxy, perhaps even encountering other civilizations along the way. Even if humanity reaches this level, it raises a profound question. Would a Type 3 civilization be able to unlock the ultimate mysteries of existence? Could they understand the true nature of the universe, uncover the secrets of dark matter and dark energy, or even manipulate the fundamental laws of physics? The Kardashev scale measures energy usage, but it does not account for the limits of knowledge. A civilization may be able to command the power of an entire galaxy, but even then, the deepest questions about reality may remain unanswered. If we ever become a Type 3 civilization, we may not just be masters of the galaxy, we may also find ourselves standing on the edge of an even greater mystery, one that no amount of energy can fully solve. Space exploration has always been one of humanity's greatest ambitions. As technology advances at a rapid pace, we find ourselves on the brink of breakthroughs that could change our understanding of the universe forever. With the continuous development of new technologies, new missions, and private companies making remarkable strides, the future of space exploration holds an exciting promise. Let's explore what lies ahead and how these advancements might shape humanity's journey through the cosmos. The rapid pace of innovation in space technology is laying the foundation for a new era of exploration. One of the most revolutionary changes in recent years has been the advent of reusable rockets. Traditionally, rockets were single-use, meaning they were discarded after each mission. This approach was not only costly, but also inefficient. However, companies like SpaceX have pioneered the development of reusable rockets. SpaceX's Falcon 9, for example, is capable of landing back on Earth after launching its payload into space, saving billions of dollars in production costs. This innovation has the potential to significantly reduce the cost of space missions, making space more accessible and opening up the possibility for more frequent missions to other planets and even beyond. In addition to rockets, there have been significant advancements in telescopes. The launch of the James Webb Space Telescope, for instance, marks a new era in our ability to observe the universe. Unlike the Hubble Space Telescope, which primarily observed visible light, the James Webb Space Telescope will focus on infrared light, allowing scientists to see through cosmic dust and peer into the earliest stages of the universe. It promises to reveal distant galaxies, exoplanets, and even potentially the origins of life itself. As the technology for space telescopes improves, our understanding of the cosmos will grow exponentially, offering unprecedented insight into the structure and history of the universe. While space exploration has historically been dominated by government agencies like NASA, recent years have seen an increasing involvement from private companies. SpaceX, founded by Elon Musk, is at the forefront of this revolution, with its ambitious goal of making space travel more affordable and ultimately enabling human settlement on other planets. SpaceX has already made history with its successful missions to the International Space Station, ISS, and it is now working on the Starship project, a fully reusable spacecraft designed for missions to the Moon, Mars, and beyond. Blue Origin, founded by Jeff Bezos, is another private company that is contributing to the future of space exploration. While it started with suborbital flights for tourists, it is now focused on developing technology for lunar exploration and building infrastructure that could support human life on the Moon. Their New Shepard rocket system is already taking payloads to space, and their future plans include the New Glenn rocket and the Blue Moon lander, which are designed to support missions to the Moon and beyond. These private companies are pushing the boundaries of space technology, competing with government agencies, and driving innovation in ways that were once unimaginable. Their efforts are lowering the cost of space travel, creating new opportunities for commercial and scientific exploration, and even inspiring a new generation of scientists and engineers to reach for the stars. Looking ahead, one of the most exciting areas of space exploration is the renewed interest in the Moon. NASA's Artemis program aims to return astronauts to the Moon by the mid-2020s, with the goal of establishing a sustainable human presence on the lunar surface. This mission will not only serve as a stepping stone for further exploration of space, but will also lay the groundwork for humanity's first attempts at colonizing other celestial bodies. In addition to the Moon, Mars continues to be the focal point for interplanetary exploration. SpaceX's Starship, designed for deep space travel, is one of the key vehicles being developed for missions to the Red Planet. In the coming years, NASA plans to send astronauts to Mars, with the first crewed mission anticipated in the 2030s. The challenges of surviving on Mars are immense, from its thin atmosphere to its harsh climate, but the potential for discovering signs of past life or even creating a human settlement is drawing immense interest. Beyond Mars, missions to the outer planets of our solar system, such as Jupiter and Saturn, are also being developed. NASA's Europa Clipper mission, set to launch in the 2020s, will investigate the icy moon Europa for signs of subsurface oceans, while the James Webb Space Telescope could reveal new details about exoplanets around distant stars. These missions are just the beginning of humanity's quest to explore the planets and moons that lie at the far reaches of our solar system. As we venture further into space, artificial intelligence, AI, and robotics will play a crucial role in the success of these missions. The vast distances involved in space travel, combined with the challenges of remote environments, make it impractical for humans to oversee every aspect of space exploration. This is where AI and robotics come into play. Robots, such as the Mars rovers, Curiosity and Perseverance, have already demonstrated the incredible capabilities of autonomous machines in space exploration. These robots are able to carry out complex tasks, collect scientific data, and even make decisions without direct human intervention. In the future, AI could help guide spacecraft, perform real-time data analysis, and even aid in the design and construction of habitats on the Moon or Mars. AI-powered systems could also help with mission planning, analyzing vast amounts of data from telescopes, satellites, and rovers, and finding patterns that humans might miss. As AI continues to evolve, it will become an indispensable tool for space exploration, enabling us to explore the cosmos more effectively and efficiently. One of the most ambitious goals for humanity is the establishment of permanent settlements beyond Earth. The idea of living on another planet is no longer confined to science fiction. With the development of new technologies and ongoing missions to the Moon and Mars, the dream of becoming a multi-planetary species is within reach. However, the challenges of colonizing other planets are enormous. Mars, with its thin atmosphere and lack of a global magnetic field, presents significant obstacles to human habitation. One of the primary concerns is radiation. Without the protective shield of Earth's atmosphere and magnetic field, astronauts and settlers on Mars would be exposed to harmful cosmic radiation, which could have serious health consequences. To address this, researchers are exploring the possibility of building underground habitats or developing radiation shielding materials to protect settlers. Another challenge is producing food and water on Mars. As Earth's resources are limited, scientists are working on technologies to grow crops in Martian soil and recycle water. But these systems will need to be highly efficient and self-sustaining to support long-term human life. Despite these challenges, the progress being made by private companies like SpaceX, NASA, and other space agencies is promising. As we continue to develop the necessary technology and knowledge, the prospect of a permanent human presence on Mars and beyond becomes more likely. One of the most profound questions that has driven space exploration is whether or not we are alone in the universe. Over the past few decades, astronomers have discovered thousands of exoplanets, many of which lie in the habitable zone of their stars, where conditions might be right for life to exist. But despite these exciting discoveries, we have yet to find definitive evidence of extraterrestrial life. Several upcoming missions are designed to address this question. The James Webb Space Telescope will be able to study the atmospheres of exoplanets in greater detail than ever before, searching for signs of life such as oxygen, methane, or other biosignatures. Missions to moons like Europa, Enceladus, and Titan will search for microbial life in their subsurface oceans. And on Mars, NASA's Perseverance rover is actively collecting samples that may one day return to Earth, potentially containing evidence of past life on the red planet. As technology advances, we may be closer than ever to answering the question of whether we are alone in the universe. These missions, along with the continuous improvement of our tools and techniques, could lead to a breakthrough discovery that changes our understanding of life itself. With all the mysteries we've uncovered, the biggest question still remains: what lies beyond the edge of our understanding? For all of human history, we have looked up at the night sky and wondered. The universe, with its billions of galaxies, countless stars, and unimaginable mysteries, has always been a source of both inspiration and confusion. Despite the incredible advancements in science and technology, the cosmos still holds secrets beyond our understanding. Each breakthrough in physics, astronomy, and space exploration brings new questions. Questions that may take centuries or even millennia to answer. But as long as we continue to explore, the quest for knowledge will never truly end. One of the most remarkable aspects of science is that every discovery expands the boundaries of what we know, while simultaneously revealing new frontiers of ignorance. When Isaac Newton formulated the laws of motion and gravity, it seemed as if we had a complete understanding of how objects move in space. Then, centuries later, Albert Einstein's theory of relativity showed us that space and time are not fixed, but bend and warp under the influence of mass and energy. This revolutionized our view of the cosmos, leading to concepts like black holes, time dilation, and gravitational waves, ideas that would have been unthinkable in Newton's time. And now, quantum mechanics has shattered our classical understanding of reality, introducing bizarre phenomena like entanglement, superposition, and wave-particle duality, concepts that defy intuition and challenge our perception of what is real. These discoveries did not close the book on physics. They opened entirely new chapters, each leading to more fundamental questions that force us to rethink everything we thought we knew. Even with all our progress, some of the greatest mysteries of the universe remain unsolved. Dark matter and dark energy make up the vast majority of the cosmos, yet we have no idea what they actually are. Despite all our observations and measurements, these two components remain elusive, shaping galaxies and accelerating the universe's expansion without us being able to detect them directly. Black holes warp space and time in ways we can barely comprehend, potentially holding the key to understanding gravity at the quantum level. Could they be gateways to other universes? Could they even be remnants of something from before the Big Bang? Speaking of the Big Bang, our understanding of the universe's birth is still incomplete. Was it truly the start of everything, or was there something before it? And if there was something before, what could that possibly mean for our understanding of existence? These are not just scientific questions, they are philosophical ones that challenge the very nature of reality. Then there is the question of life. We know that Earth harbors an astonishing diversity of living organisms, all originating from a common ancestor billions of years ago. But is life unique to our planet, or is it scattered throughout the universe? The discovery of even the simplest alien microbes would fundamentally change our perspective on biology and evolution. If intelligent civilizations exist, then the implications are even more profound. What would it mean for humanity to know that we are not alone? Would we be prepared for such a revelation? And if we never find extraterrestrial life, does that mean we truly are unique, or simply that we have not looked in the right places? The search for life beyond Earth is one of the greatest scientific endeavors of our time, pushing us to develop new technologies, send probes to distant moons, and scan the skies for signs of communication. Exploration has always been at the core of human nature, from the earliest nomadic tribes venturing into unknown lands to the modern-day missions probing the depths of the cosmos. Curiosity drives us forward. The James Webb Space Telescope is already revealing distant galaxies from the dawn of time, giving us glimpses into the universe's earliest moments. Plans for Mars colonization, interstellar probes, and even theoretical warp drives continue to push the limits of what is possible. With advancements in artificial intelligence, quantum computing, and nanotechnology, the future of exploration might unfold in ways we cannot yet predict. We might soon have telescopes capable of directly imaging Earth-like exoplanets, spacecraft powered by nuclear fusion capable of reaching the outer solar system in record time, or even the first permanent human settlements beyond Earth. But with every step forward, we are reminded of how much we still do not know. The observable universe may be 93 billion light-years wide, but it is only a fraction of what may truly exist. If space is infinite, then so are the possibilities for discovery. Even time itself may not be as linear or absolute as we once thought. Could there be other dimensions, parallel realities, or unknown cosmic forces shaping our fate? Could the laws of physics themselves be different in other parts of the universe, governed by unknown principles we have yet to uncover? These questions, once considered science fiction, are now subjects of serious scientific inquiry. And what about the distant future? Will humanity survive long enough to see the end of the universe? Or will we go extinct long before we reach that point? Civilization, as we know it, is fragile, and countless existential threats, from asteroid impacts to climate change, from pandemics to nuclear war, could wipe us out before we ever achieve interstellar travel. But if we do survive, what will we become? Could we harness the energy of entire stars, entire galaxies? Could we create artificial worlds, reshape reality itself, and transcend the limitations of biology? Could we one day merge with technology and exist as digital consciousness, free from the constraints of flesh and bone? The possibilities are as limitless as the universe itself. What will we discover next? Perhaps we will find evidence of life on an exoplanet orbiting a distant star. Perhaps we will uncover new particles that revolutionize our understanding of physics. Maybe one day, humanity will set foot on another world, taking the first steps toward becoming an interstellar species. Or perhaps we will face challenges we cannot yet foresee. Existential threats, cosmic events, or limitations in our own understanding that prevent us from advancing further. The one certainty is that the journey of discovery will never truly end. As long as there are questions to be asked, as long as the universe remains vast and mysterious, we will continue to seek answers. We may never fully understand everything, but that is what makes the pursuit of knowledge so extraordinary. The universe does not owe us its secrets, but we will never stop searching for them. And in that endless search, we may just find something even greater than answers. We may find purpose, wonder, and the boundless potential of the human spirit. Perhaps that, more than anything, is what makes us unique in this vast cosmic ocean. The ability to dream, to explore, and to never stop reaching for the stars.